In January 1972, a commercial flight operated by Jet Airways was the target of a bomb attack. The explosion in the cargo hold split the plane in half at an altitude of approximately 10,160 meters. All 27 passengers and crew members died, except for one person, Vesna Vulovic, a 22-year-old flight attendant who, through an extraordinary combination of physiological, structural, and circumstantial factors, survived a free fall of over 10 kilometers. She fractured her skull, legs, and vertebrae, and remained in a coma for days, but her heart kept beating. The Guinness Book officially recorded the event as the highest fall without a parachute that a person has survived. The inevitable question from a scientific perspective is, how is this possible? And what does the human body reveal to us in these rare cases where death seems certain, yet doesn't occur? Vesna was strapped to her seat in the rear of the aircraft, which crashed on a snowy hillside in a village of the former Czechoslovakia. It is believed that the impact was partially cushioned by a combination of soft snow, vegetation, and the angle at which the fuselage hit the ground. But even with these factors, any medical evaluation would suggest that the abrupt deceleration, multiple injuries, and the time it took for rescue would make her chances of survival nearly zero. However, there are physiological factors that, although rarely aligned in this way, can create a statistical loophole in which life clings to the impossible. One such factor is hypothermia induced by altitude. The sudden drop in body temperature may have slowed Vesna's metabolism quickly, reducing oxygen demand and protecting vital tissues during the trauma and rescue. This phenomenon is well documented in emergency medicine. The colder a trauma victim is, the higher the chance of preserving brain function if rescue is fast. Another surprising aspect involves the type of injuries sustained. Multiple spinal fractures like those suffered by Vesna typically lead to paralysis or death if the spinal cord is involved. However, in her case, the fractures occurred in regions that, though severe, allowed for surgical stabilization and partial neurological recovery. The cranial trauma was serious, but did not cause irreversible damage to brain areas responsible for vital functions. Moreover, she was found by a trained first responder, a former army physician who lived nearby and managed to stabilize her until emergency services arrived. This detail is more important than it seems. The time between trauma and the initiation of life support measures is a determining factor in survival rates for extreme accidents. Medical science classifies survivors like Vesna as physiological outliers. These are individuals who, through an unusual combination of anatomy, inflammatory response, physical constitution, accident context, and early assistance, cross the threshold of death without actually passing it. Later studies revealed that Vesna had abnormally low blood pressure before the accident, a factor that, according to trauma specialists, may have reduced the risk of brain hemorrhage by limiting circulatory force at the moment of impact. Furthermore, there are suspicions that she was trapped inside a metallic section of the fuselage that acted like a cocoon, redistributing the impact energy and preventing direct crushing of the chest and head, two areas that are typically fatal in high-speed falls. The case of Vesna Vulovic is widely studied in emergency medicine and trauma courses as an extreme example of human resilience. Beyond the miracle that many invoke, biology sees a set of small variables that rarely align but prove that the human body, under certain conditions, can successfully defy the laws of probability and physics. Her story also contributed to the development of improved trauma protocols in fall-related incidents, demonstrating that survival may be possible even in situations where rescuers typically do not expect to find life. Science continues to investigate such cases to better understand the limits of human endurance, the role of the immune response in trauma, and the physiological mechanisms we still don't fully comprehend, but which, under extreme pressure, may emerge as the final resource of a body determined to survive. When a human body enters free fall from high altitudes, the experience is not only terrifying, it is physiologically extreme. At elevated heights, such as the over 10,000 meters that separated Vesna Vulovic from the ground, the body faces a series of near-instant critical challenges. The first is the lack of oxygen. At altitudes above 8,000 meters, atmospheric pressure is so low that the air becomes hypobaric, with almost no oxygen available for effective respiration. This results in anoxic hypoxia, a total deprivation of oxygen in the brain that, in healthy humans, causes loss of consciousness in less than 30 seconds. This is one reason why many victims of aerial falls never perceive the full fall. Early fainting, paradoxically, can act as a neurological defense against extreme terror and acute psychological suffering. During the fall, gravitational acceleration pulls the body toward the ground at approximately 9.8 meters per second squared. However, the human body does not accelerate infinitely. There is a point at which air resistance balances out gravity, the so-called terminal velocity, which for an average adult in a belly-down position is about 190 km/h. If the body is in a vertical or more aerodynamic position, that velocity can exceed 300 km/h. At such speeds, impact with any solid surface would almost always be instantly fatal, but there are exceptions. If the fall is broken by vegetation, rooftops, deep snow, or even structures that deform upon impact, the deceleration can be spread across crucial fractions of a second, enough to change the outcome between life and death. Another key factor in the physiology of free fall is the internal trauma caused by sudden deceleration. Even when there are no visible external fractures, the internal organs continue moving due to inertia and may slam against internal body structures. The brain in particular faces the risk of contusions, subdural hemorrhages, and diffuse axonal injury, all of which compromise consciousness and vital functions. The heart may rupture, the lungs may collapse, the liver, one of the most vascularized organs, may tear upon impact. All of this depends on how the body hits the ground, the nature of the surface, and how kinetic energy is dissipated. The position of the body during the fall also influences physiological outcomes. Skydiving experts train students to assume the odd belly-down position with arms and legs spread, which increases air resistance and reduces terminal velocity. Falls involving rotation, such as those caused by explosions, lead to uncontrollable spins that prevent any instinctive attempt at body stabilization. In such cases, the body hits the ground with random extremities, which may either spread impact force across multiple points or concentrate it on vulnerable areas such as the cervical spine or base of the skull, typically fatal. Science also recognizes a phenomenon known as lucky break trajectory, fall paths in which, by random chance, the body encounters successive obstacles that progressively slow it down, such as trees, sloped hillsides, or collapsing structures. These elements, though unpredictable, create a multi-stage deceleration that allows the body to endure trauma that would otherwise be fatal in a direct impact. Medical literature includes rare cases of survivors who landed on power lines, construction scaffolding, or parked vehicles, all of which help to absorb the shock in an unintentional but crucial way. In extreme scenarios, the hypothermia induced seen by high altitude and falling speed can also have protective effects, as discussed earlier. When the body cools rapidly, metabolism slows, and the demand for oxygen by vital organs decreases. This extends the window of time during which the brain can survive without full oxygenation, essential in cases of severe trauma where blood flow is impaired. In cold environments, this state can develop during the fall itself, especially in high-altitude flights or sub-zero climates. Finally, it is important to note that surviving free fall is not merely a statistical lottery. Although cases like Vesna-Vulovic are exceedingly rare, they provide valuable insights into how the human body behaves in extreme situations. Each survivor offers real-world data about the CT biomechanical and neurological limits of the body, pushing scientists to rethink what is considered incompatible with life. These insights feed back into research in areas such as surgical trauma, aerospace medicine, gravitational physiology, and emergency response protocols in hostile environments. Ultimately, studying what happens to the body in free fall is a study of the outer edge of human vulnerability and resilience. In the late 1980s, one of the most remarkable cases of extreme survival captured the attention of the medical world, that of Jan Hilliard, a young Canadian woman who was found completely frozen after spending hours exposed to temperatures below -30 degrees Celsius on a winter night in Minnesota. She had driven off the road in a minor accident and attempted to seek help by walking several kilometers through the snow. Exhausted, She collapsed unconscious near a friend's house and was discovered only the next morning lying rigid like a statue with pale, crystallized skin that needles could not penetrate. Paramedics reported that the body was so frozen they were unable to insert anything into the skin. And yet, in a manner that bordered on the supernatural, Jean not only survived, she recovered fully, with no neurological damage or limb loss. Science had to turn its attention to this phenomenon. What actually happens when a human body freezes to that extent? And how is it possible to reverse that state? To understand the case, it's essential to grasp the mechanism of profound hypothermia, a state in which the body's core temperature drops below 28 degrees Celsius. In this range, the body's metabolic activity slows so drastically that oxygen consumption falls to less than 25% of normal levels. The heart beats more slowly, the brain enters a kind of dormancy, and vital organs operate at minimal function. In Jean's case, it is believed her collapse occurred while her body temperature was still above the threshold for irreversible cellular death, which paradoxically allowed her to freeze from the outside in a controlled manner. Additionally, the exposure to cold was not abrupt, as in the case of falling into icy water, but gradual, allowing the body to enter a sort of involuntary physiological hibernation. Medicine recognizes this state as a form of metabolic preservation. Under extreme and prolonged cold, cellular activity slows, reducing the production of free radicals, preventing massive inflammation, and preserving the function of structures such as the central nervous system. When cooling is homogeneous and the patient does not suffer repeated cardiac arrests, there is a chance, albeit small, of reversing the condition through slow and carefully monitored rewarming techniques. That is precisely what happened with Jean. Doctors chose to wrap her in heated blankets and administer warm oxygen gradually, avoiding abrupt temperature changes that could trigger thermal shock or cardiovascular collapse. The process took hours, with continuous monitoring. When her heart began to beat spontaneously again, the medical team could hardly believe what they were witnessing. Freezing itself poses a lethal risk, primarily because as the water inside cells turns to ice, it expands and can rupture cell membranes. This is the greatest barrier to survival in deep freezing, the internal structural damage caused by crystallization. However, in some cases like Jean's, the ice appears to have formed primarily in the extracellular space, while the cells retained some natural osmotic protection. This hypothesis is supported by studies on animals that enter hibernation, in which the production of endogenous glycerol or other cryoprotectants prevents the formation of lethal ice crystals inside cells. Although humans do not have this capability to any significant degree, it is believed that Jean's extremely slowed metabolism, combined with a favorable body composition and a slow cooling rate, partially simulated this protective mechanism. This event is not isolated. Medical literature records other similar cases, such as that of Anna Bogenholm, a Swedish skier who survived over an hour submerged in -2 degrees Celsius water beneath a sheet of ice. With her core body temperature reduced to 13.7 degrees Celsius, one of the lowest ever recorded in a human with complete recovery. Cases like Jean Hilliard's and Anna's challenge the traditional boundaries of the clinical definition of death. In states of extreme hypothermia, the heart may stop, the brain may show no detectable electrical activity, but the organism is not yet dead, merely suspended. This realization led to the creation of modern resuscitation protocols built on the phrase, "A hypothermic patient is not dead until warm and dead," meaning that death can only be confirmed after controlled rewarming fails to restore life. Modern science studies these cases not merely as extreme curiosities, but as windows into potential medical innovations, such as therapeutic hypothermia, to preserve brain function after cardiac arrest, or complex surgeries performed with extracorporeal circulation. They also inspire research in cryogenics, organ cryopreservation, and even future deep sleep protocols for space travel. Jean Hilliard's case is remembered as a turning point, proof that the human body, when immersed in utterly hostile conditions, can activate biochemical pathways that are still poorly understood, yet capable of challenging medical certainties and redefining the boundaries of life. The popular image of extreme cold is almost always associated with slow and inevitable death. However, in emergency medicine and human physiology, there exists a counterintuitive truth. Cold, under certain conditions, can save lives instead of taking them. This phenomenon, known as protective hypothermia, has been studied for decades and is supported by both extraordinary clinical cases and controlled experiments with patients undergoing cardiac arrest, neurological trauma, or highly complex surgical procedures. The core of this mechanism lies in how body temperature directly affects the speed of biochemical reactions, oxygen demand, and overall cellular metabolism. When the body is cooled in a controlled or gradual way, it enters a state of extreme economy, capable of preserving vital structures even under conditions normally incompatible with life at standard body temperature. The concept is not new. During World War II, military doctors observed that severely wounded soldiers who remained in cold environments for long periods had surprisingly higher chances of surviving deep injuries than those rescued immediately in warm conditions. In the 1950s, the first documented experiments on therapeutic hypothermia began to appear, especially in cardiac surgeries. By deliberately lowering a patient's body temperature before stopping blood circulation, doctors were able to extend the amount of time the brain remained viable without oxygen. Later studies confirmed that for every degree Celsius below 37 degrees, brain oxygen consumption drops by about 6%, unveils, allowing patients to withstand longer periods of ischemia, that is, total absence of blood flow. In natural cases of freezing, such as Jean Hilliard's, the body enters deep hypothermia involuntarily, but the physiological principle is similar. Exposure to intense cold reduces electrical brain activity, slows the heart rate, and minimizes cellular energy needs. This state is neither painless nor inherently safe. It requires a delicate balance. If the cooling is too rapid, abrupt thermal damage can occur, such as peripheral tissue injury and intracellular crystallization. But if it's gradual, and the individual has a favorable metabolic constitution, the cold transforms into a kind of temporary biological suspension. Modern medicine has learned to simulate this condition using thermal control equipment, cooling blankets, intravenous catheters with chilled fluid, and cold air ventilation to reduce body temperature systematically and safely. The use of hypothermia as a medical tool is now primarily applied in three critical situations: post-cardiac arrest, severe traumatic brain injury, and high-risk neurosurgeries. In patients who have suffered a cardiac arrest and were successfully resuscitated, the risk of irreversible brain damage is highest within the first few hours. The therapeutic hypothermia protocol calls for cooling the body to about 33 degrees Celsius for 24 to 48 hours, followed by gradual rewarming. This process reduces the risk of cerebral edema, limits the release of toxic neurotransmitters such as glutamate, and lowers the production of free radicals. Clinical studies show that patients who undergo this protocol have a significantly higher rates of functional neurological recovery than those who do not receive induced cooling. Neuroscience also explores the effects of hypothermia in conditions such as ischemic strokes, intracranial hemorrhages, and refractory seizures. By lowering the brain's temperature, researchers observe a neuroprotective effect that can prevent the death of millions of neurons during the critical hours after an acute event. In animal model experiments, rats subjected to hypothermia after brain injury showed superior motor and cognitive recovery, with less inflammation and cellular apoptosis. While the effects in humans remain under continuous study, the data suggest that controlled cooling may be a valuable tool for preserving the integrity of the central nervous system. But not everything about hypothermia is beneficial. Even when induced, it carries considerable risks. It can cause cardiac arrhythmias, coagulopathies, opportunistic infections, electrolyte imbalances, and if not reversed precisely, can lead to death. For this reason, centers that use this technique do so under strict protocols and with intensive monitoring in critical care units. Success depends on the timing of induction, the depth of hypothermia, the patient's pre-existing clinical condition, and the speed of rewarming. Even so, the idea that cold can preserve rather than destroy defies conventional thinking and offers a fascinating perspective on the adaptive mechanisms of the human body. In research, studies on hypothermia have expanded far beyond hospital emergencies. Scientists working on organ cryopreservation for transplants, use similar principles to keep kidneys, livers, and hearts viable for longer periods outside the body. In projects related to space exploration, NASA and other agencies are investigating ways to induce prolonged torpor states through mild hypothermia in astronauts, a technique that could allow long-duration missions with lower energy consumption and reduced physiological degradation. What began as an extreme response of the body to the environment has become a therapeutic tool, a field of study, and a window into the future of human medicine. Under normal conditions, the human body is designed to function with a constant intake of nutrients. Prolonged absence of food triggers a series of physiological and metabolic responses that, while initially aimed at survival, soon begin to compromise vital functions. Even so, medical history documents numerous cases of individuals who, by choice or under extreme circumstances, survived for weeks or even months without food, challenging the known limits of human biology. Some of these cases occurred during wars, others in shipwrecks, concentration camps, political hunger strikes, or accidents in remote areas. One of the most notable examples is that of E. Angus Barbieri, a Scottish man who, under medical supervision in 1965, survived for 392 days without consuming any solid food, ingesting only water, black coffee, and vitamin supplements. He lost over 120 kilograms and maintained stable cognitive and organ functions. Cases like his provide science with a rare opportunity to observe how the human metabolism reacts under conditions of complete caloric deprivation. The body's first response to food absence is the consumption of glycogen stores, a form of glucose stored primarily in the liver and muscles. This reserve typically lasts between 12 and 24 hours in average individuals. Once depleted, the body enters a state known as lipid catabolism, where energy is obtained by breaking down fat. Triglycerides stored in adipose tissue are converted into fatty acids and ketone bodies, which become the primary energy source for the brain, muscles, and internal organs. This stage, known as ketosis, is the same targeted by ketogenic diets, but during prolonged fasting, it occurs more intensely and continuously. The body enters a sort of economy mode, lowering its metabolic rate, adjusting hormonal output, and prioritizing basic survival functions. During long-term fasting, the body must also minimize the breakdown of structural proteins, such as muscles and organs. This is managed through a series of delicate hormonal adjustments. Insulin levels drop drastically, while glucagon, adrenaline, and cortisol levels rise. Thyroid function is reduced to conserve energy. Body temperature may decrease slightly, and menstrual cycles in women may be interrupted. Muscle mass begins to degrade only in the later stages of starvation, once fat reserves are nearly depleted. Even so, the human brain demonstrates remarkable adaptability. During prolonged ketosis, it can derive up to 75% of its energy from ketone bodies, reducing its reliance on glucose and enabling fasting to continue for surprisingly long periods. Historical cases reinforce these findings. During hunger strikes, such as those led by political prisoners in Northern Ireland in the 1980s, many fasters survived between 45 and 70 days without food, with death usually resulting from liver failure or secondary infections rather than starvation itself. In World War II concentration camps, there are reports of prisoners surviving on caloric intakes of fewer than 400 calories a day for over 6 months, enduring extreme muscle wasting, vitamin deficiencies, and neurological injuries, but maintaining vital signs. The human body, though visibly degraded in such contexts, demonstrates a metabolic resilience capable of sustaining life under minimal energy conditions, something that still intrigues modern endocrinology. One of the greatest dangers of prolonged fasting is the so-called refeeding syndrome, a potentially fatal condition if food is reintroduced too quickly after extended deprivation. When a deeply fasting individual receives glucose and nutrients abruptly, there is a sudden metabolic shift. Insulin levels spike and essential electrolytes such as phosphorus, potassium, and magnesium are driven into cells. This can lead to arrhythmias, seizures, and even heart failure. Therefore, all clinical cases of refeeding after extreme starvation require slow, progressive, and closely monitored nutritional reintroduction, with micronutrient supplementation beginning even before carbohydrates are reintroduced. After weeks or months without food, the human body must relearn how to digest and metabolize safely. From a scientific standpoint, extreme fasting is increasingly being studied through the lens of cellular longevity and metabolic regeneration. Research in animals and humans shows that controlled periods of fasting, even short ones, can activate autophagy mechanisms, increase resistance to oxidative stress, improve insulin sensitivity, and even stimulate stem cell renewal. This emerging field, known as intermittent caloric restriction, is being explored as a potential tool for delaying aging and preventing metabolic diseases. However, absolute fasting for months, as in the extreme cases discussed here, remains a high-risk frontier, something that should only occur in hospital settings with therapeutic justification or intensive monitoring. The human body's ability to survive without food for extended periods challenges our intuitive understanding of hunger physiology. Cases like Angus Barbieri's and those of survivors of war and accidents should not be romanticized, but studied as rare examples of extreme adaptation. They demonstrate that the human body is more plastic than we previously believed, capable of entering deep energy conservation modes, reorganizing internally, and preserving life in biologically unsustainable conditions. Understanding these mechanisms helps medicine expand its therapeutic arsenal, anticipate risks, and explore the unknown edges of human biology, where, even without nourishment, the organism finds ways to endure. The survival of the human body, in a state of extreme fasting, is a delicate dance between degradation and preservation. When deprived of nutrients for prolonged periods, the organism enters a kind of controlled metabolic crisis, in which its biological machinery is reorganized with the sole objective of preserving life. This reorganization involves multiple systems: endocrine, cardiovascular, nervous, and immune. Every cell in the body must adapt to scarcity, shutting down non-essential processes, prioritizing vital tissues, and reshaping energy consumption. In this context, metabolism does not collapse immediately. It retracts, restructures, recalibrates, and it is this deep plasticity that allows human beings to survive even without nutrients for weeks or months. The first stage of metabolic crisis begins shortly after circulating glucose, and hepatic glycogen stores are depleted, typically between 12 and 24 hours after fasting begins. From that point on, the body activates gluconeogenesis, a process by which the liver and kidneys synthesize glucose from non-carbohydrate sources, such as amino acids from muscle tissue, glycerol from fat breakdown, and lactate. This emergency glucose is directed primarily to the brain, which at this stage still heavily depends on it. However, since continuous protein breakdown quickly compromises lean mass and organs, the body soon shifts to a more efficient and less destructive pathway: fatty acid oxidation and ketone body production. Ketone bodies, especially beta-hydroxybutyrate, become the main players in this metabolic crisis. Produced in the liver from fatty acids released by adipocytes, these compounds can cross the blood-brain barrier and fuel the brain directly, replacing much of the glucose demand. By making this transition, the body protects its muscle tissues and reduces protein catabolism. This is one reason why individuals with ample fat reserves can survive longer during starvation. They possess a dense energy supply that can be mobilized over weeks. Simultaneously, the basal metabolic rate, KRICHA, the amount of energy the body uses at rest, drops significantly in an effort to slow the consumption of remaining stores. During this adaptive phase, the hormonal system undergoes profound changes. Insulin secretion reaches minimal levels, while glucagon, the emergency energy hormone, takes control. The hypothalamic pituitary adrenal axis is activated, increasing cortisol release, which mobilizes energy reserves, but also comes at a cost. It promotes muscle degradation and suppresses the immune system. Leptin, the satiety hormone, plummets. Ghrelin, which stimulates hunger, rises. Sleep-wake cycles may be altered, as may body temperature, which tends to drop slightly to conserve calories. In women, amenorrhea, cessation of menstruation, is common, as the reproductive system is temporarily silenced. As fasting extends, the body enters a phase of minimal damage maintenance. This stage is marked by selective activation of autophagy, a cellular process that recycles damaged organelles and accumulated proteins. Autophagy is a survival mechanism that prevents programmed cell death and keeps basic cellular function going with limited resources. From an evolutionary standpoint, this mechanism likely developed as a way to ensure internal maintenance during times of food scarcity, prolonging an individual's viability until the next meal. Recent studies suggest that autophagy is not only essential for surviving fasting, but also for preventing neurodegenerative diseases, inflammatory conditions, and even cancer. However, this balance is finite. In very prolonged fasts, typically beyond 60 to 90 days, fat stores are also depleted, and the body begins to consume vital structures: the heart, liver, and respiratory muscles. Severe protein malnutrition leads to generalized edema, immune collapse, liver failure, cardiac arrhythmias, and serious neurological impairments. Even though the brain adapts to using ketones, it suffers from a lack of essential micronutrients such as thiamine, magnesium, zinc, and B-complex vitamins. The blood-brain barrier loses integrity, and opportunistic infections become common. This is the tipping point of metabolic crisis, when the cost of maintenance exceeds the body's adaptive capacity. And yet, some survivors defy this threshold, and science still seeks to understand which genetic, hormonal, and environmental factors make such extreme resilience possible. Today, this deep understanding of metabolism under deprivation influences various fields of medicine. Intermittent caloric restriction protocols are used in therapies for cancer, autoimmune diseases, and metabolic disorders. Controlled induction of mild catabolic states through 24 to 72-hour fasting is being studied as a way to enhance autophagy and improve insulin sensitivity. In intensive care units, understanding the high adaptive metabolic phase is critical for determining when, how, and how much to feed critically ill patients without triggering refeeding syndrome. Thus, the same mechanisms that allow survival under extreme scarcity are being activated in clinical settings with precise therapeutic goals. Therefore, a metabolism in crisis is not merely a system on the verge of collapse. It is a flexible and finely tuned architecture, capable of enduring weeks of total deprivation through cascading adjustments, activation of ancestral pathways, and complete redefinition of biological priorities. Studying how the body survives without nutrients also means exploring the hidden potential of human physiology, not only to understand the extremes of survival, but to open doors to therapies that use controlled deprivation as a tool for healing. Few events trigger such a rapid and lethal sequence of physiological failures as drowning. The abrupt interruption of oxygen flow to the brain, combined with the mechanical collapse of respiration, makes death by submersion one of the most dramatic conditions, until recently considered almost irreversible after just a few minutes. Yet, modern medical literature has documented cases that challenge this idea. Stories in which individuals submerged for 10, 20, or even 60 minutes were rescued, resuscitated, and survived with preserved neurological functions. These cases are not only shocking due to their improbability, but they also offer valuable clues about the limits of the human body under extreme hypoxia, and how, under certain conditions, the dying process can be delayed or even reversed. The physiology of drowning follows a well-defined sequence. In the first seconds of submersion, the instinct is to hold one's breath. As carbon dioxide accumulates and the respiratory reflex kicks in, water is inhaled, triggering a power laryngospasm, a reflex that closes the airway to prevent liquid from entering the lungs. In some cases, this temporarily prevents pulmonary aspiration, but leads rapidly to loss of consciousness. If the larynx relaxes, water enters the lungs, immediately compromising gas exchange. Intense cerebral hypoxia begins to kill neurons in about 4 to 6 minutes. At this stage, cardiac arrest, either from ventricular fibrillation or a systole, is imminent. Without resuscitation, death typically follows within minutes. However, science has learned that some variables can alter this trajectory. One of the most powerful is water temperature. Submersion in cold water, especially below 5 degrees Celsius, triggers the time-to-cold water immersion reflex, an ancestral human response that lowers heart rate, constricts peripheral vessels, and redirects blood flow to vital organs. This reflex, more pronounced in children and young people, can induce a state of extreme bradycardia and reduced metabolism, extending the window of time for resuscitation. There are documented cases of children submerged for over 30 minutes in frozen lakes who were revived with little or no brain damage, cases that have revolutionized the medical understanding of the so-called point of no return after submersion. A famous example is Anna Bogenholm, a Swedish physician who, after a skiing accident in 1999, became trapped under a layer of ice in a frozen stream for about 80 minutes. When she was rescued, her core temperature was around 7 degrees Celsius, considered incompatible with life. Yet she was transported to a hospital and resuscitated using extracorporeal circulation machines, gradually recovering without permanent cognitive impairment. This case became a landmark in post-drowning resuscitation protocols, showing that, in cold environments, submersion time alone cannot dictate when to stop rescue efforts. Medicine now classifies drowning into two main categories: warm water drowning, where neurological damage occurs more quickly, and cold water drowning, where the body may enter a preservation state induced by hypothermia. In both cases, the speed of resuscitation is critical. Modern techniques involve immediate cardiopulmonary resuscitation, advanced ventilatory support, continuous temperature monitoring, and in specific cases, the use of ECMO, extracorporeal membrane oxygenation, a machine that temporarily takes over heart and lung function, oxygenating the blood outside the body while the patient is maintained in full life support. Beyond respiratory failure, drowning causes profound disruptions in the body's acid-base balance. The retention of CO2 and severe metabolic acidosis are harmful to the nervous system and heart muscle. Therefore, successful reversal requires more than restoring breathing. It demands precise correction of electrolytes, temperature, and tissue perfusion. A common mistake in resuscitation attempts is rapid rewarming, which can cause abrupt vasodilation, hypotension, and fatal arrhythmias. That's why modern protocols insist on passive and progressive rewarming, with continuous monitoring of intracranial pressure, cerebral oxygenation, and kidney function. Recoveries after prolonged drowning remain rare, but they are critical in reshaping the concept of clinical death. Rather than a fixed marker, medicine now recognizes that death, in cases of submersion, can be a reversible process for longer than previously thought, especially when cold is involved. This new perspective has influenced international guidelines for first aid, aquatic rescue, and advanced resuscitation. It has also inspired research into how metabolic modulation through hypothermia or pharmaceuticals might protect the brain in other anoxic conditions such as heart attacks, strokes, and major trauma. Drowning, as lethal as it seems, has become one of the richest fields for studying neuroprotection, prolonged resuscitation, and the boundaries of life. Every patient saved after long minutes underwater provides science with a key that opens the door to better understanding the mechanisms of survival under extreme conditions, the silent adaptations of the human body, and perhaps a future in which the thresholds between life and death can be controlled with more precision than ever before. The drowning process does not end with submersion, it begins there. When water enters the airways and invades the pulmonary alveoli, it instantly compromises the exchange of vital gases. Oxygen, essential for sustaining cellular life, can no longer pass into the bloodstream, and carbon dioxide ceases to be expelled. This respiratory interruption triggers a cascade of failures, beginning in the lungs, advancing to the cardiovascular system, and culminating in the collapse of the central nervous system. Water, therefore, doesn't kill merely by physically occupying the lungs, but by causing a systemic hypoxia, a profound metabolic acidosis, and rapid destructive brain dysfunction. Understanding each stage of this progressive failure allows medicine not only to treat cases more effectively, but to anticipate complications and identify potential points of reversal, even after cardiac arrest. The moment water enters the lungs, it washes away the pulmonary surfactant, a substance that lines the alveoli and prevents them from collapsing during respiration. Without surfactant, the alveolar walls collapse like deflated balloons, making oxygen intake even more difficult. Additionally, water increases the permeability of pulmonary vessels, leading to acute pulmonary edema, the accumulation of fluid in the gas exchange spaces. Blood passing through these capillaries cannot be oxygenated, and systemic oxygen saturation plummets. In response to this hypoxia, the heart increases its rate in an attempt to compensate. But this effort only accelerates oxygen consumption, creating a vicious cycle of metabolic suffocation. Meanwhile, the brain is among the first organs to suffer the effects of hypoxemia. With just 5 seconds of total oxygen deprivation, brainwave activity begins to change. In 30 seconds, consciousness is lost. After 2 to 3 minutes, the most sensitive neurons, such as those in the hippocampus, begin to die. Acidosis, caused by CO2 buildup and a shift to anaerobic metabolism, disrupts cellular enzyme function and accelerates structural injury. Moreover, the entry of water into the lungs alters blood electrolyte balance, especially depending on whether the water is fresh or salt. Fresh water, when absorbed into capillaries, may cause hemolysis, destruction of red blood cells. Salt water, on the other hand, draws water out of vessels, concentrating the blood and worsening circulatory shock. The heart, deprived of oxygen and burdened by intense acidosis, begins to fail. Initially, this manifests as tachycardia, but it soon deteriorates into ventricular arrhythmias, such as fibrillation or asystole, complete cessation of electrical activity. The myocardium is extremely sensitive to blood pH. Even minor fluctuations can destabilize calcium and potassium channels, which are essential for rhythmic heart contractions. Blood pressure collapses, organ perfusion ceases, and the brain enters a state of irreversible ischemia unless intervention occurs. At this stage, the body is clinically dead, but science has learned that this clinical death is not necessarily final if the chain of events can be interrupted in time with advanced support. Survival outcomes depend on how quickly water is removed from the lungs and circulation and oxygenation are restored. Resuscitation begins with DAG-assisted ventilation using 100% oxygen, often followed by orotracheal intubation to ensure air reaches the lungs. Positive pressure ventilation helps reopen collapsed alveoli and expel some of the fluid. At the same time, acid-base and electrolyte imbalances must be corrected through carefully calculated intravenous infusions. In the most severe cases, extracorporeal membrane oxygenation, ECMO, is used to oxygenate the blood outside the body, allowing the lungs to recover while protecting the brain from hypoxia. Beyond respiratory and cardiovascular resuscitation, brain care becomes the top priority in the following hours. The so-called post-drowning syndrome includes risks of cerebral edema, seizures, respiratory infections, and progressive neurological injuries. Therefore, even when victims are successfully revived, they must be monitored in intensive care units with neuroprotective support, thermal control, and constant evaluation of cerebral perfusion. The introduction of therapeutic hypothermia has shown promising results in this context. By reducing the body's temperature to around 33 degrees Celsius, physicians can lower brain metabolism and increase the likelihood of functional recovery. Although water entering the lungs is the most dramatic factor in drowning, full recovery is possible if the physiological stages are understood and treated rapidly. Modern medicine now acknowledges that death from drowning is not a fixed event, but a stepwise process, and each of these stages, from pulmonary collapse to brain damage, offers an opportunity for reversal. Extreme clinical cases continue to demonstrate that even when the heart stops and the brain falls silent, life can be brought back if the right support is given in time. And each of these stories continues to redefine the limits of what is biologically possible. In 2007, neurologists in China published a case study that left the scientific world perplexed. A 24-year-old woman, seemingly healthy, was admitted to the hospital with mild symptoms of dizziness and instability. Upon performing imaging tests, the medical team discovered something that seemed impossible. She lacked the left cerebellar hemisphere of her brain, a region responsible for coordinating movement, balance, and motor precision. There were no signs of surgery or trauma. She had been born this way, and yet she could walk, speak, study, and live independently. This case was not unique. Over recent decades, multiple medical reports have documented people living with partial or total absence of brain structures, from the cerebellum to parts of the cerebral cortex, while still exhibiting near-normal cognitive function. How is this possible? The answer lies in one of the most extraordinary capacities of the human brain: neuroplasticity. Neuroplasticity is the nervous system's ability to reorganize its synaptic connections, reallocating functions to different areas when lesions, surgical removals, or congenital malformations occur. This capacity is especially strong in childhood, when the brain is still developing and holds a much greater reserve of plasticity. When a brain region is damaged or missing from birth, other areas, often in the opposite hemisphere, can take over its functions. This adaptation occurs both structurally and functionally. Axons grow in new directions, synapses are reinforced along alternative pathways, and even regions traditionally linked to specific functions can begin operating in new roles. Extreme cases of this brain reorganization have been documented in patients who underwent hemispherectomy, a radical surgical procedure in which half of the brain is removed to treat intractable epilepsy. Remarkably, many of these individuals, especially if operated on during childhood, are able to walk, speak, study, and engage socially with considerable ease. Although they may have motor limitations on the side opposite the removed hemisphere, their cognitive functions often remain within normal ranges. This challenges the classical neurological paradigm that assigned fixed, immutable functions to specific brain regions. The Chinese woman's case also highlights something crucial. The brain not only compensates for structural deficits, but can grow and function through alternative circuits from early life. In her congenital absence of the left cerebellar hemisphere, the right hemisphere had subtly enlarged and assumed compensatory roles. Brainstem nuclei also showed adaptations, with increased fiber density in typically less active regions. This anatomical reorganization might not be perfect. The patient displayed slightly slurred speech and difficulty with fine motor tasks, but her degree of autonomy was nonetheless remarkable. Cases of extreme hydrocephalus, a condition where the brain is compressed by accumulated fluid inside the skull, further support this notion. There are documented reports of adults living into old age with only 10% of normal brain volume, rate exhibiting average IQs and leading functional lives. In such cases, the cerebral cortex is reduced to a thin layer lining the skull, yet still manages to sustain perception, language, and consciousness. The explanation lies in the brain's ability to distribute functions in a decentralized manner, adapting to adverse conditions with surprising efficiency. Modern science is attempting to understand the limits of this plasticity. Functional MRI studies have shown that patients with congenital brain lesions exhibit cortical activation in unusual regions during motor and cognitive tasks. For example, individuals born without Broca's area, traditionally associated with speech production, can activate other areas of the frontal lobe to form sentences. Language, memory, and consciousness appear to be more distributed than previously thought, operating through flexible networks that can reorganize in response to necessity. This discovery has direct implications for neurological rehabilitation. Today, techniques such as a transcranial stimulation, adaptive virtual reality, and intensive occupational therapy aim to tap into this residual plasticity in patients with strokes, trauma, or neurodegenerative diseases. In children with early lesions, intensive interventions can shape the developing brain to recover lost functions. Even in adults, once considered less plastic, new evidence shows that forced learning and intense environmental stimulation can induce structural brain changes. The woman missing part of her brain is not just an anatomical exception. She is a living example of how the human brain is less a rigid machine and more a living adaptive system. Every neuron, every synapse, every glial cell contributes to a dynamic balance that, in the face of adversity, can find alternative paths to preserve identity, memory, movement, and even consciousness. Studying these extreme cases allows neuroscience not only to better understand the brain, but also to develop new ways of treating those whose injuries, once thought irreversible, now mark the beginning of a new functional reorganization. Strokes, also known as cerebrovascular accidents, CVAs, have been for decades one of the leading causes of death and disability worldwide. When a stroke occurs, it abruptly cuts off the blood supply to a portion of the brain, leading to rapid cell death in the affected region. Traditionally, it was believed that the functional loss resulting from a stroke was permanent. However, over the past 2 decades, a growing body of studies and clinical cases has revealed a much more complex phenomenon. The injured brain can reconfigure itself, reorganize its functions, and recover capabilities once thought lost. This rediscovery of brain plasticity in adults has radically transformed the medical understanding of neurological rehabilitation, showing that even after severe damage, the brain never completely stops trying to rebuild itself. A stroke can be ischemic, caused by the blockage of a cerebral artery, or hemorrhagic, caused by the rupture of a blood vessel within the brain. In both cases, the immediate damage leads to the loss of motor, speech, vision, or cognitive functions, depending on the affected area. What neurologists began to observe is that, even after entire areas of the cortex became non-functional, other regions, including those in the opposite hemisphere, began to show increased activity and signs of functional reorganization. This reconfiguration is neither instantaneous nor automatic. It depends on stimuli, intensive rehabilitation, and most importantly, a critical window of weeks to months after the event, during which the brain is most responsive to adaptation. The basis of this phenomenon lies in the cellular mechanisms of adaptive neuroplasticity. After a stroke, neurons near the damaged area, and sometimes even in distant regions, can form new synaptic connections in an attempt to compensate for lost functions. Axons may slowly grow toward damaged areas, while dendrites expand their branches to seek new contacts. In addition, glial cells and the brain's immune system participate in cleaning and rebuilding, removing dead tissue and facilitating a favorable environment for synaptic regeneration. This phenomenon, observed in both humans and animal models, is influenced by factors such as age, lesion size, overall health, and the intensity of therapeutic interventions. Extreme clinical cases illustrate this adaptive potential. There are documented patients who, after massive strokes, completely lost the ability to speak, walk, or recognize family members, yet with intensive rehabilitation, partially or even fully recovered these functions over the course of months or years. Modern fMRI techniques have shown that in these individuals, areas previously uninvolved in speech or movement begin to activate during those tasks. The brain, quite literally, recreates alternative pathways to achieve the same result. In some cases, this even involves the recruitment of brain structures not originally associated with those functions. For example, redirecting language processing to the right hemisphere in patients with extensive damage to the left. Science is also exploring therapies that enhance this plasticity. One of the most promising is transcranial magnetic stimulation, TMS, which uses electromagnetic fields to activate specific brain regions and encourage the recruitment of compensatory areas. Another emerging technique is transcranial direct current stimulation, TDCS, which modulates the excitability of neurons near the lesion site. Both methods have shown significant results in accelerating the recovery of motor and language functions when combined with intensive physical and speech therapy. Moreover, the unintensity of motor practice following a stroke directly influences brain reconfiguration. Studies have shown that patients who perform thousands of targeted movement repetitions, even if flawed, over weeks exhibit greater recruitment of compensatory areas and synaptic reinforcement. This supports the idea that the brain responds to functional demand with structural adaptation. The motto, "Use it or lose it," has become central to rehabilitation neurology. More recently, the concept of forced motor learning, such as in constraint-induced movement therapy, has been successfully applied in hemiparetic patients, compelling them to use the affected side and forcing the brain to relearn motor pathways. The study of survivors of severe strokes has expanded not only the horizon of functional recovery, but also our understanding of brain circuits as dynamic and redundant systems. The old view of the adult brain as static has given way to a model in which adaptation is continuous, though slower with age. This feeds new strategies for secondary prevention, neuroprotective interventions in the early stages of stroke, and the development of neural prosthetics capable of directly interacting with recovering brain circuits. The reconfiguring brain is not a rare phenomenon or one restricted to mild cases. It is a real and increasingly explored possibility in modern medicine. By studying cases where recovery once seemed impossible, science discovers tools for all others. Patients whose injuries once appeared permanent, but who now, through technology, rehabilitation, and deep understanding of neuroplasticity, have a real chance to restore part of what was lost. These survivors teach us that, even after the destruction of old pathways, new routes can be forged, and that the brain, even when wounded, keeps searching for ways to continue being who we are. Among the most striking cases in emergency medicine are those in which the human skull is penetrated by blunt or sharp objects, accidents involving rebar, stakes, knives, projectiles, and even industrial tools, in situations that, at first glance, seem absolutely incompatible with survival. And yet, there are rigorously documented clinical reports of patients who not only survived these extreme traumas, but retained intact cognitive, motor, and sensory functions. Medicine refers to them as neurosurgical miracles, but behind the shock and dramatic visuals lie physiological, anatomical, and surgical explanations that reveal how resilient, reorganizable, and compensatory the human brain can be, even under the most devastating injuries. The classic case illustrating this capacity is that of Phineas Gage, an American railroad worker who, in 1848, had his skull pierced by an iron rod over 1 meter long. The rod entered through his left cheek, traversed the skull base, passed through the left frontal lobe, and exited through the top of the skull. Despite the severe injury, Gage not only survived, he walked and spoke within minutes of the accident. His case remains one of the most studied in neuroscience, as it marked the beginning of the modern understanding of brain function localization and the behavioral consequences of frontal lobe injuries. However, what continues to astonish is that he did not die from brain hemorrhage, infection, or cardiopulmonary arrest, factors almost always fatal in similar cases. How was this possible? The key to survival in such cases often lies in the exact trajectory of the object, which, incredibly, can pass through the brain without damaging vital areas. The human brain contains regions of varying functional density. Some areas, like the brainstem, thalamus, and skull base, house nuclei responsible for vital functions, breathing, heartbeat, consciousness. Other areas, such as parts of the frontal or parietal lobes, may be injured with limited or compensable effects. When an object enters the skull along a path that avoids these critical zones, survival becomes a real possibility. The accidental anatomy of the injury, therefore, becomes one of the primary determinants of outcome. Another fundamental factor is the immediate control of intracranial pressure and infection. Objects that remain lodged in the skull must be removed with extreme caution in a surgical setting, as premature extraction can cause catastrophic bleeding. In many cases, neurosurgeons choose to stabilize the patient, conduct high-resolution imaging, and plan the surgery with micrometric precision. The use of neuronavigation techniques, continuous monitoring of cerebral perfusion, and broad-spectrum antibiotics has significantly increased survival rates. In specialized hospitals, penetrating skull injuries from metal or wooden objects have survival rates above 50% when there is rapid access to surgery and proper post-operative infection control. Recent cases further highlight the brain's plasticity in the face of trauma. In 2012, a construction worker in Brazil survived after a 2-meter iron rod pierced his skull vertically. The object passed through the right hemisphere without hitting eloquent areas such as Broca's area, Wernicke's area, or the primary motor cortex, and was successfully removed following a complex craniotomy. The patient had an impressive neurological recovery. In another case in the United States, a woman survived the penetration of a construction rebar that entered through the orbital bone and traversed both cerebral hemispheres diagonally. After months of rehabilitation, she regained her ability to speak and walk. These cases also underscore the importance of the brain's functional reserve. Even when a lesion affects critical areas, the brain can reorganize its functions in neighboring regions, or even in the opposite hemisphere, provided it is correctly stimulated during rehabilitation. Neuroplasticity, already mentioned in earlier sections, is especially intense after acute injuries, and can be guided through occupational therapy, magnetic stimulation, physiotherapy, and intensive task-specific training. The presence of neural stem cells in certain brain regions, such as the dentate gyrus of the hippocampus, also contributes to the recovery of damaged circuits, though this process is not yet fully understood. Clinically, the main complications in penetrating cranial trauma are intracranial hematoma terescus, progressive cerebral edema, infection from meningitis or abscess, and post-traumatic seizures. These factors, if not managed, can be fatal even after a successful surgery. For this reason, patients are monitored for weeks in intensive care units with serial neurological exams, electroencephalograms, and follow-up neuroimaging. Many require long-term anticonvulsants, cognitive rehabilitation, and in some cases, reconstructive surgeries to repair the skull using titanium plates or bone grafts. Despite the apparent severity, penetrating brain injuries show that the brain is more resilient and adaptable than once believed. Survival depends not only on the extent of the damage, but on its location, the speed of medical intervention, the quality of neurosurgery, and the brain's capacity to reorganize itself in the weeks that follow. These cases challenge not only the physiological limits of life, but also our concepts of what constitutes a functional brain. They force us to consider that, even when pierced by a lethal object, the human brain can rebuild itself, layer by layer, synapse by synapse, in search of the continuity of consciousness and life. Among the most radical procedures in modern neurosurgery is the hemispherectomy, an intervention in which one of the cerebral hemispheres, right or left, is partially or completely removed to control catastrophic epilepsies. At first glance, the idea of living with only half a brain seems impossible. After all, each hemisphere is responsible for essential motor, cognitive, and sensory functions. And yet, hundreds of patients, especially children, live today with only one hemisphere and maintain two surprisingly high levels of functionality. These cases are not only astonishing from a clinical standpoint, they reveal the extraordinary adaptive capacity of the human brain, particularly during its developmental phase, and continue to redefine the neurological limits of life. Hemispherectomy is typically indicated for patients with severe epilepsy, such as Rasmussen syndrome or unilateral brain malformations, where seizures are daily, drug-resistant, and devastating to development. In such conditions, the affected hemisphere not only fails to contribute to brain function, but also acts as a constant source of epileptic activity, compromising the healthy side. The surgery thus aims to remove or disconnect the dysfunctional hemisphere, to allow the remaining side to take full functional control. In adults, this surgery is rarely performed, but in children, especially those under 8 years old, the results are remarkable. Many regain the ability to walk, speak, study, and even participate in sports, despite the anatomical absence of half the brain. The explanation lies in childhood brain plasticity, which peaks in the early years of life. During this phase, neurons are highly adaptable, and entire regions can be recruited to take over functions originally assigned to other areas. When a hemisphere is removed early, the remaining hemisphere expands its connections, reorganizes circuits, and redirects motor, linguistic, and cognitive activities. The classic brain lateralization, in which the left hemisphere governs language and the right controls visuospatial functions, partially dissolves, allowing functions to be redistributed according to demand. This means that a child with a left hemispherectomy can still learn to speak fluently, and one with a right hemispherectomy can develop adapted spatial perception. Neuroimaging studies such as fMRI and PET-CT show that this functional reorganization is visible. The remaining areas display functional hyperactivity, a sign that they are compensating for tasks previously handled by the absent hemisphere. Connectivity scans reveal the growth of alternative internal communication pathways, notably involving the corticospinal and associative tracts that adapt to the new configuration. In many cases, the cortex of the intact hemisphere even thickens in certain regions, as a trophic response to increased demand. Despite these strong functional outcomes, predictable consequences do occur. The most common is contralateral hemiparesis, or weakness on the side opposite the removed hemisphere. This weakness may range from mild to moderate, and is typically more evident in fine motor skills, such as writing or manipulating small objects. Another common consequence is partial loss of the opposite visual field, hemianopia, since the crossed visual pathways are also affected. Still, the brain learns to compensate for these deficits through sensory reorganization, adaptive learning, and behavioral strategies. Most impressively, in many cases, IQ remains within normal range or decreases only slightly, a remarkable feat considering the magnitude of the anatomical surgery. Post-hemispherectomy rehabilitation is lengthy but highly effective. Intensive programs involving physical therapy, occupational therapy, and speech-language therapy are essential for maximizing recovery. Many children undergo years of training, reinforcing compensatory circuits and developing adaptive skills. Over time, the brain becomes more efficient in its new configuration, and what was initially a functional challenge becomes the new normal. Documented cases show adult patients who have lived more than 40 years after a childhood hemispherectomy, with active professional lives and full social integration. From both a philosophical and scientific perspective, these cases challenge the notion that consciousness and identity require a complete brain. Hemispherectomy patients report dreams, emotions, moral decisions, memories, and a stable sense of self, central elements of the human experience. The absence of half the cortex does not prevent the individual from having an intact I. This reinforces the idea that the mind emerges from dynamic and distributed networks, and that even a reduced brain structure can sustain the full complexity of human experience. For neuroscience, hemispherectomy cases are a fertile research ground for understanding functional redundancy, cortical reorganization, and the minimal thresholds of conscious thought. They also inform studies on adult brain injury recovery, early stimulation strategies, and in the future, adaptive neural prosthetics that might simulate this plasticity in damaged brains. In the end, these patients not only survive, they rewrite our understanding of what a functional brain is and prove that, even with half the structure, the brain can still be whole, with careers, social relationships, and levels of autonomy comparable to those of individuals without brain injuries. One Canadian patient, operated on at age 5, became a math teacher. Another, in the United States, studied engineering and reports only mild difficulties with fine motor coordination. These accounts challenge traditional ideas of the brain as a fixed and irreplaceable organ in its functional distribution. They point instead to a more elastic concept, that of a modular and trainable brain, capable of reallocating its functions under pressure and reorganizing itself in response to loss. The success of a hemispherectomy also depends on factors beyond age: the rate of progression of the underlying disease, the degree of seizure control after surgery, the preservation of subcortical structures, and the quality of the rehabilitation environment are all determining elements. Children with strong family support, access to regular therapies, and positive school integration tend to achieve significantly better outcomes. Conversely, even after a successful surgery, patients who lack sufficient stimulation during the postoperative phase may regress or develop global developmental delays. This underscores that the brain, no matter how plastically prepared it may be, requires demand, practice, and continuous stimulation to fully adapt. In research, hemispherectomy has become a valuable source of data for understanding how the mind works. Studying individuals with only one functioning hemisphere allows scientists to observe how brain functions are redistributed in alternative ways. Some patients exhibit, for instance, enhanced capacities for selective attention or verbal memory, suggesting that the brain, when forced to operate within a smaller space, can become more efficient at certain neural tasks. Others display changes in emotional lateralization, such as a reduced response to stress or alterations in processing affective stimuli. While these observations are still under deeper investigation, they suggest that the brain does not merely compensate for losses, sometimes it reinvents itself. Hemispherectomy cases also serve as reference models for developing less invasive interventions, such as partial disconnections, neurostimulation therapies, and intensive functional retraining for patients with strokes, tumors, or malformations. By mapping how the brain reorganizes motor, sensory, and cognitive functions in extreme cases, medicine is learning to guide this adaptation more efficiently in localized injuries. The data also contribute to the development of brain-computer interfaces, as they demonstrate how alternative regions can be recruited to control robotic limbs or communication systems in patients with severe paralysis. Ultimately, hemispherectomy is more than a life-saving surgery. It is a living proof of the brain's radical flexibility. Even in the face of losing half its volume, the brain finds a way. It rebalances, rebuilds, reprograms. It shows that what defines our mental capacity is not only the original anatomy, but also the ability to adapt in the face of adversity. Studying these cases brings us closer to understanding the hidden mechanisms of consciousness, language, memory, and resilience, revealing that, when forced to choose between stopping and changing, the brain almost always chooses to change in order to keep being. Prolonged exposure to extreme heat is one of the most severe physiological endurance tests for the human body. Unlike cold, which slows down metabolic processes and can sometimes preserve the body under specific conditions, intense heat accelerates all systems chaotically. In environmental temperatures exceeding 45 degrees Celsius, as frequently seen in the Sahara, Australian deserts, or urban regions under extreme heat waves, the body is pushed to the limits of thermoregulation. And yet, there are documented reports of people surviving in environments surpassing 70 degrees Celsius for hours, maintaining consciousness, and, in some cases, even walking kilometers under direct sunlight. These extraordinary cases are studied closely by medicine and environmental physiology, as they reveal just how far the human body can go before collapsing from hypothermia. The normal core body temperature is approximately 37 degrees Celsius. When this temperature surpasses 40 degrees Celsius, early signs of severe hypothermia appear: mental confusion, muscle fatigue, tachycardia, nausea, flushed skin, and excessive sweating. Above 41.5 degrees Celsius, the risk of irreversible neurological damage increases exponentially. If the temperature reaches 42 degrees Celsius, cellular proteins begin to denature and organ systems start to fail. However, there are clinical records of survival with core temperatures as high as 44 degrees Celsius, particularly among soldiers, industrial workers, and individuals lost in desert environments. The central question for science is, how can the body, in some cases, remain functional even when immersed in this level of thermal assault? The key lies in a series of extreme thermoregulatory mechanisms, primarily coordinated by the hypothalamus. When the ambient temperature exceeds body temperature, the primary route for heat dissipation, sweating, becomes essential. The body begins producing liters of sweat per hour, and the evaporation of this sweat enables latent heat loss. But for this process to be effective, the air must be dry and circulating, which explains why high humidity is more dangerous than dry heat. In environments like the Sahara, where humidity can drop below 10%, evaporation is intense, allowing the body to maintain its temperature longer, even under direct sun exposure. Another critical factor is physiological adaptation to chronic heat, known as thermal acclimatization. People who have lived for years in extremely hot regions develop more efficient bodily responses. Increased blood plasma volume, earlier onset of sweating, more efficient redistribution of blood flow to the skin, and even changes in the electrolyte composition of sweat. These adaptations enable heat to be dissipated with less cardiac strain, reducing the risk of circulatory collapse. Science has observed that Saharan nomads, Bedouins, and heavy foundry workers clearly demonstrate these modifications. Their survival rates in extreme heat are significantly higher than those of the general population. There's also the role of behavioral and cognitive resilience. In many cases of extreme desert survival, success depends not only on physiology, but also on strategy. Reducing physical activity, wearing lightweight and reflective clothing, remaining immobile during peak heat, and hydrating with small amounts at regular intervals are behaviors that increase the chances of survival. Interestingly, some cases report that intense thirst can disappear after a certain point, a serious sign of hypothalamic dysfunction and imminent failure. Individuals who maintain critical awareness, even in the early stages of hypothermia, have better chances of adjusting their behavior and avoiding collapse. Medical science also examines cases of rescue from overheated environments, such as victims trapped in closed vehicles under the sun or underground mine workers. In some of these instances, core body temperature surpasses 42 degrees Celsius, yet recovery using rapid cooling techniques, such as immersion in cold water or cooling catheters, prevents neurological damage. Current protocols indicate that survival in severe hypothermia depends on how quickly temperature is reduced in the first few hours, requiring it to fall below 38 degrees Celsius in less than 90 minutes to avoid widespread cellular death. Patients who exceed this threshold are at risk for rhabdomyolysis, kidney failure, and disseminated intravascular coagulation. Documented cases of survivors from heat storms in India, Australia, and the United States show that, despite its narrow limits, the human body possesses emergency metabolic pathways to cope with heat. Some studies have observed the activation of heat shock proteins, which help preserve cellular integrity in extreme environments. Research is also investigating the role of genetics in heat tolerance. Certain individuals appear to carry variants that enhance sweat efficiency, peripheral vasodilation, and mitochondrial resistance to heat. Surviving extreme heat remains one of the most intense frontiers of human physiology. Studying the mechanisms that allow life to persist under elevated temperatures is not merely an academic curiosity. It's an urgent necessity in a world where climate change is making heat waves increasingly frequent and deadly. Understanding how the body responds, adapts, and in some cases, withstands the impossible is one of modern science's core missions, not just to save individuals at risk, but to prepare humanity for an increasingly hotter future. Few human experiences are as painful, rapid, and devastating as being trapped inside a fire. The combination of extreme heat, toxic gases, respiratory collapse, and deep thermal trauma usually results in death within minutes. And yet, there are documented cases of people who survived intense fires, with over 80% of their bodies burned, compromised airways, multiple cardiopulmonary arrests, and pain beyond what human consciousness is believed to tolerate. These stories, though dramatic, are a rich source of insight for medical science, revealing how the body tries to resist total destruction when the skin, lungs, and nervous system are assaulted simultaneously. In these extreme survivors, medicine finds clues about the limits of physical suffering, tissue regeneration, and the neurochemistry of pain. The skin, the body's largest organ, is the first line of defense against heat. In structural fires, temperatures can exceed 600 degrees Celsius within minutes. When skin reaches 48 degrees Celsius, proteins begin to denature. Above 55 degrees Celsius, cellular destruction is nearly instantaneous. Third-degree burns destroy all layers of the skin, affecting nerves, blood vessels, and potentially penetrating muscles and bones. At this level, the initial pain can be intense but is soon replaced by localized anesthesia, not as relief, but because the pain receptors have been destroyed. Even so, surrounding regions remain hyperstimulated, and the brain is bombarded with unbearable distress signals. The pain of extensive burns is considered among the most intense ever recorded in clinical studies, with many patients reporting vivid memories even under deep sedation. In fires, the heat doesn't only affect the skin. The upper airways are quickly damaged by inhaling superheated air, soot, carbon monoxide, and cyanide, released from burning synthetic materials. This hot air burns the mucosa of the mouth, trachea, and bronchi, causing obstructive edema that can close off the airways within minutes. Exposure to carbon monoxide displaces oxygen from hemoglobin, creating cellular hypoxia even when the patient appears to be breathing adequately. Cyanide, in turn, blocks the mitochondrial respiratory chain, halting cellular energy production. The sum of these effects can lead to unconsciousness, respiratory arrest, and death even before the flames touch the skin. In survivors, the body enters systemic inflammatory collapse. Massive tissue destruction releases inflammatory mediators like interleukins and TNF-alpha, leading to vasodilation, increased vascular permeability, and massive fluid loss. The patient quickly goes into hypovolemic shock, with plummeting blood pressure and risk of multi-organ failure. Moreover, the body's natural barriers are gone. The skin that once protected against infection has vanished. Even after thermal stabilization, these patients face high risks of sepsis, necrosis, fungal and bacterial infections. all potentially fatal. Surviving extensive burns requires heroic interventions. The first hours are critical. The globally used Parkland protocol dictates the amount of intravenous fluids a patient must receive to prevent circulatory collapse. Deep sedation and aggressive pain management follow, often requiring powerful analgesics like ketamine, fentanyl, or propofol. The patient is stabilized in a controlled environment with artificially elevated ambient temperature, as the loss of skin impairs thermoregulation. Mechanical ventilation is often needed due to airway edema or smoke inhalation. The reconstruction process is long and grueling. Skin grafts, reconstructive surgeries, repeated debridements, and occupational therapy become routine for months or years. Skin regeneration depends on advanced biotechnology, such as bioengineered grafts, autologous skin cultivation, and artificial dermal matrices. Even so, healing is not only physical. Most patients develop severe psychological disorders, such as post-traumatic stress, depression, anxiety, and often a redefined body image marked by visible scars and permanent dysfunctions. Despite all this, there are documented cases of impressive functional and emotional recovery. A notable example is J.R. Martinez, an American soldier who survived burns over 34% of his body during the Iraq War, underwent more than 30 reconstructive surgeries and became an actor, speaker, and symbol of resilience. Cases like his, and many others, anonymous patients in burn centers worldwide, are studied not only by medicine, but also by psychology, pain neuroscience, and biomedical engineering. To science, every survivor of a severe fire is a living window into the absolute limits of suffering, regeneration, and the persistence of consciousness. They reveal that the human body, even under the total destruction of its outer structure, can activate emergency survival routes and fight for weeks, months, sometimes years to rebuild itself. And that behind the burns, the dressings, and the intensive therapies, there is a nervous system, striving to protect the most essential thing of all, the sense of being alive. Ionizing radiation is invisible, silent, and at high doses, deadly. It passes through tissues, breaks molecular bonds, damages DNA, and can trigger a biological collapse in a matter of hours or days. Yet medical history records emblematic cases of individuals exposed to theoretically fatal levels of radiation, who, instead of dying instantly, survived for weeks, sometimes months, under intensive clinical monitoring. These temporary survivors of extreme radiation became living laboratories of cellular destruction, allowing science to document step by step how atomic energy silently disintegrates a still conscious human body. The most well-known case is that of Hisashi Uchi, a Japanese technician involved in the Tokaimura nuclear accident in 1999. Uchi was exposed to an estimated 17 sieverts of radiation, enough to kill a human within minutes. However, due to rapid medical intervention, his body was kept alive for 83 days in an intensive care unit, while his biology progressively collapsed. His blood stopped regenerating, his skin detached in large sheets, and systemic infections took over his body. Despite the brutality of the situation, science was able to observe the effects of radiation in real time, from bone marrow failure to DNA strand breaks to the disintegration of the immune system. Ionizing radiation acts on tissues by stripping electrons from atoms and molecules, generating highly reactive free radicals. These particles initiate a cascade of cellular damage that primarily affects tissues with high renewal rates, skin, bone marrow, intestinal mucosa, and reproductive organs. Acute radiation syndrome, ARS, manifests in phases. In the first hours, symptoms include nausea, vomiting, headache, and diarrhea. This is followed by a deceptive latent period where symptoms temporarily vanish, but the cellular destruction continues. After a few days, the crisis phase begins. The immune system collapses, platelets drop, white blood cells vanish, and the risk of hemorrhage and infection becomes imminent. The body attempts to fight back. In Uchi's case, doctors used bone marrow transplants, cutting-edge antibiotics, daily transfusions, and full support for kidney, liver, and respiratory function. However, the radiation had damaged the genetic code of nearly every dividing cell. Cellular regeneration became impossible. The intestine, another rapidly renewing tissue, began to ulcerate and necrotize. The skin, unable to produce new layers, started to peel off in sheets. Auchi developed multiple organ failure, and yet his brain remained lucid for days, a disturbing paradox in which consciousness witnesses the destruction of its own body. Cases like this, though rare, are not isolated. Survivors of the Chernobyl and Fukushima accidents, nuclear lab technicians and doctors exposed to radioactive materials before protective standards were adopted, have all contributed to the advancement of knowledge on radiation's effects in humans. In Chernobyl, workers known as liquidators were exposed to doses ranging from 1 to 16 sieverts, experiencing everything from cataracts and infertility to leukemia and rare neurological syndromes. A considerable number of patients survived for years, enabling long-term studies on genetic mutations, radiation-induced carcinogenesis, and chronic immune alterations. Nuclear medicine has also benefited from this extreme knowledge. Based on radiation's lethal effects, targeted therapies for cancer were developed, such as intensity-modulated radiotherapy, which uses controlled doses to selectively destroy tumors. The key difference lies in beam precision and the amount of energy absorbed measured in grays, GY, and sieverts, SY. Still, the principles remain the same. Radiation breaks cell DNA, and if cells can't repair the damage, they enter apoptosis, programmed cell death. What kills us in high doses can, in microdoses, heal us. Physiologically, death by radiation is unique. Unlike trauma or infection, it shuts the body down from the inside out, first attacking renewal systems, then defense mechanisms, and finally, the structural integrity of tissues. Death is almost always due to sepsis, massive hemorrhage, or multi-organ failure. In extreme cases, such as patients exposed to more than 20 sieverts, death can occur within hours, leaving no room for medical response. But between those extremes lies a zone where medicine can intervene, and where science gathers precious data on human resilience. These radioactive survivors, even if only for a limited time, reveal how far a cell can endure genetic chaos, how long skin can last without renewal, and how long consciousness can persist in a disintegrating body. They are witnesses to radiation's silent horror, but also gateways to understanding the invisible frontiers of life. Among all technological disasters in history, the nuclear accidents of Chernobyl, 1986, and Fukushima, 2011, are among the most studied, not only for their environmental and social impacts, but for what they revealed about radiation's effects on the human body. In both cases, workers and emergency teams were exposed to extreme levels of ionizing radiation over short periods. These individuals developed, with varying intensities, acute radiation syndrome, ARS, a devastating clinical condition in which the body's cellular systems begin to fail systematically. Each of these victims became a case study in how radiation's invisible energy targets human blood, skin, intestines, bones, brain, and DNA at fatal levels. ARS begins silently. In the first minutes to hours after exposure to a dose above 1 gray GY, non-specific symptoms emerge: nausea, vomiting, dizziness, and headaches. These signs mark the prodromal phase and are often ignored by workers who continue to be exposed without realizing the severity. In Chernobyl, firefighters sent in without protective gear began showing symptoms while still battling the flames. After this stage comes a latency phase, which may last from hours to days, during which symptoms subside and the patient appears to recover. But this is an illusion. During this time, radiation begins destroying rapidly dividing cells, such as those in the bone marrow, gastrointestinal tract, and oral mucosa. Bone marrow destruction is one of ARS's central pillars. Radiation halts cell division and causes apoptosis in the progenitor cells of red and white blood cells and platelets. This leads to severe anemia, immune suppression, and extremely high risk of spontaneous bleeding. The patient enters a state of pancytopenia, defenseless against infection, without adequate oxygenation, and without effective blood clotting. This condition demands daily transfusions and, in critical cases, bone marrow transplant attempts, as done with several Chernobyl victims, though with limited success. Radiation also damages vascular endothelium, increasing vessel permeability and triggering circulatory shock and multiple organ failure. The gastrointestinal tract suffers intense damage. The epithelial cells of the small intestine, which renew every 24 hours, are extremely sensitive to radiation. Their destruction results in ulceration, hemorrhaging, loss of the mucosal barrier, and bacterial translocation into the bloodstream. Patients develop severe diarrhea, abdominal pain, uncontrollable vomiting, and dehydration. The condition rapidly progresses to sepsis, worsened by marrow-induced immunosuppression. In Chernobyl, several workers died from acute intestinal infections combined with respiratory and kidney failure. In Fukushima, lower exposure levels avoided such extreme outcomes, but clinical data collected confirmed ARS's cellular destruction pattern. The skin is also affected. High-dose radiation causes radiation burns that do not appear immediately. After days, blisters, epidermal necrosis, deep peeling, and intense pain emerge. These wounds are slow to heal and often require grafts and surgical repair. In Chernobyl, the hands of some firefighters and workers were completely disfigured due to direct exposure to reactor graphite. In severe cases, necrotic skin becomes an infection source, further worsening systemic conditions. The central nervous system is only directly affected at extremely high exposures, above 30 grays. At this level, acute neurovascular syndrome causes seizures, loss of consciousness, cerebral edema, and death within hours. This was observed in Chernobyl in extreme cases, such as technicians inside the reactor control room at the moment of the explosion. For most victims, however, neurological effects are secondary and appear later as consequences of systemic infection, hypoxia, and multi-organ damage. Among survivors, records show chronic cognitive impairment, memory disorders, insomnia, and mood disturbances, possibly linked to chronic radiation-induced inflammation. Treating ARS is complex and multidisciplinary. It involves absolute patient isolation, hemodynamic support, blood transfusions, broad-spectrum antibiotics, antifungals, antivirals, parenteral nutrition, strong analgesia, and, in selected cases, bone marrow transplants. In Tokaimura and Fukushima, modern techniques were used, such as hematopoietic growth factors, to stimulate marrow recovery and biological decontamination protocols. Still, the ARS mortality rate at high doses remains high, between 60% and 100%, depending on exposure level and speed of intervention. For science, each case of acute radiation syndrome is a map of progressive human physiological collapse, but also a source of knowledge on hematological regeneration, DNA repair, systemic inflammatory response, and the limits of homeostasis under extreme aggression. Data collected from nuclear disasters inform everything from emergency protocols to cancer therapies and radiological protection studies in astronauts. And above all, they show that even when the body is surrounded by invisible destructive energy, it fights with every cell, molecule, and electrical signal to stay alive one more day. Pain is one of the most universal and, paradoxically, most subjective experiences of the human body. It emerges from a complex network of peripheral receptors, nerve fibers, spinal ganglia, and brain centers that interpret injuries, inflammation, or internal dysfunctions as threats. However, there are documented clinical cases of patients who, even after severe injuries to the central or peripheral nervous system, and even with partial absence of essential neurological structures, continue to report intense, chronic, and often unbearable pain. These extreme episodes challenge the classical understanding of pain neurophysiology and push science to explore a deeper, more diffuse dimension of human suffering. Pain that persists even when there is no nerve, tissue, or detectable physical stimulus remaining. One of the most emblematic situations in this context is the phenomenon known as phantom limb pain. This condition occurs in amputees who, even after the complete removal of an arm, leg, or finger, continue to feel pain, itching, tingling, or muscle contractions in a part of the body that no longer exists. Studies indicate that around 80% of amputees experience this phenomenon, which can last for months or years. What is surprising is that even in the physical absence of the limb, the brain continues to receive signals as if it were still present and injured. The explanation lies in the maladaptive plasticity of the somatosensory cortex. where body maps are preserved even after limb loss. When neighboring areas take over the cortical space previously occupied by the representation of that limb, a perceptual short circuit occurs, which is interpreted as pain. Another extreme case involves patients with complete spinal cord injuries. In theory, a total transverse lesion, as seen in paraplegic and quadriplegic individuals, should prevent any communication between the brain and body segments below the injury. Yet many of these patients report severe pain in regions that, neurologically speaking, are disconnected. This pain, known as central pain, does not depend on peripheral stimuli, but instead arises from the spontaneous activity of neurons in the spinal cord or thalamus that fire pain signals without sensory input. It is as if the brain, deprived of normal information, begins generating false threat signals, interpreted as pain that cannot be located, measured, or silenced by conventional analgesics. The situation becomes even more complex when observing patients with complex regional pain syndrome, CRPS, a rare condition in which small injuries to peripheral nerves trigger a disproportionate response from the autonomic and central nervous systems. The affected area, often a hand or foot, becomes extremely sensitive with continuous pain, temperature changes, color alterations, sweating, and involuntary movements. In many cases, the pain persists even after nerve blocks, amputations, or complete nerve pathway sectioning. The brain again appears to perpetuate the pain through its own roots. Functional imaging scans show excessive activation in regions such as the insular cortex, anterior cingulate cortex, and amygdala, centers linked to emotion, attention, and pain memory. In such cases, pain is not merely a sensory phenomenon, it is also an emotional and mnemonic state. Pain also persists in cases of severe encephalopathies. Patients in minimally conscious states, vegetative states, or with brain regions damaged by trauma or ischemia may still exhibit physiological responses to pain. Increased heart rate, pupil dilation, sweating, and muscle contractions in response to noxious stimuli. Studies using EEG and fMRI reveal that even in partially destroyed brains, there are neural networks that respond to painful stimuli, even if the subjective experience of pain cannot be verbalized. This raises complex ethical questions regarding pain management in non-communicative patients, such as those in intensive care units, comatose states, or with advanced neurodegenerative diseases. For medicine, understanding pain without a complete physical structure is both a technical and philosophical challenge. In these cases, pain appears to arise not from the peripheral body, but from disorganized or excessive activity within the central nervous system. This has led to the development of therapies that go beyond nerve blocks and aim to modulate the brain. Transcranial stimulation, spinal cord neuromodulation, biofeedback, immersive virtual reality, guided meditation, and the controlled use of psychedelic substances are being studied as ways to re-educate the brain about the body. The goal is not merely to suppress pain, but to rebuild the internal body map, allowing the nervous system to abandon pathological signaling patterns. What these extreme cases teach us is that human pain is not a simple response to physical stimuli. It is an emergent, complex phenomenon that integrates sensation, memory, expectations, emotions, and language. When the nervous system is fragmented, amputated, or injured, it does not stop feeling. It may feel even more, for it no longer has a reference point. Pain in these damaged bodies becomes a cry without origin, but with a very real echo, one that may last a lifetime. And understanding this is not only a clinical task, it is an act of listening, science, and humanity in the face of one of the most intense mysteries of biological existence. For a long time, it was believed that after 5 minutes without a heartbeat, the chances of resuscitation with preserved brain function were virtually zero. This estimate was based on the rapid degradation of neurons without oxygen, leading to irreversible brain death. However, extraordinary cases recorded in emergency medicine in recent decades have challenged this paradigm. There are confirmed reports of patients who remained in cardiac arrest for over an hour without spontaneous circulation and were still brought back with neurological functions intact. These episodes are not just miraculous, they are clinical laboratories. They serve as windows into understanding how far the human body can tolerate the absence of apparent life before the brain shuts down forever. The first key to understanding these seemingly impossible recoveries lies in deep hypothermia. In situations where cardiac arrest occurs in very cold environments, such as drowning in frozen lakes or skiing accidents, the rapid drop in body temperature can drastically slow down metabolism. This reduces tissue oxygen consumption and extends the time window for resuscitation without neurological damage. The saying in trauma centers, "No one is dead until they are warm and dead," captures this principle. Cases like that of Swedish skier Anna Bogenholm, who was revived after more than 60 minutes submerged in water at 2 degrees Celsius, are still studied today as manuals for reversing functional death. However, the phenomenon is not limited to hypothermia. In hospital settings, advances in technology and resuscitation protocols have made it possible to reverse prolonged cardiac arrest even at normal temperatures. This is due to devices like ECMO, extracorporeal membrane oxygenation, which temporarily takes over the function of the heart and lungs, maintaining blood flow and oxygenation while the cause of the arrest is investigated and treated. In 2019, a widely documented case in medical literature involved a 34-year-old French woman who suffered cardiac arrest while climbing in the Pyrenees. She was kept on ECMO for over 6 hours without spontaneous heartbeats, and after rewarming and full support, recovered without neurological sequelae. The success of resuscitation after prolonged arrest depends on a series of interdependent factors. The first is the quality of CPR, cardiopulmonary resuscitation. Continuous chest compressions with the correct rhythm and depth can maintain minimal cerebral perfusion for several minutes. Experimental studies show that this residual perfusion is enough to keep neurons alive in a low-activity state. Additionally, the time between arrest and the start of resuscitation is critical. Each minute without CPR reduces the chance of survival with intact brain function by 10%. For this reason, the presence of trained responders, automated defibrillators, and rapid response protocols exponentially increases the chances of recovery. Another key factor is post-resuscitation care. Even after spontaneous circulation is restored, the brain remains vulnerable to reperfusion injury, a phenomenon in which the reintroduction of oxygen causes intense inflammation, oxidative stress, and secondary cell death. To mitigate this risk, induced therapeutic hypothermia is applied, cooling the body to 33 degrees Celsius for up to 48 hours, reducing brain activity and preventing edema. Studies show that patients treated with this protocol have significantly higher survival rates with good neurological outcomes. The combination of effective compressions, advanced support, and post-resuscitation thermal control now forms the backbone of cardiovascular emergency centers of excellence. Even more impressive cases involve patients with refractory ventricular arrhythmias who underwent CPR for over 45 minutes with vasoactive drug support, and who, after the underlying cause, such as acute myocardial infarction, pulmonary embolism, or overdose, was reversed, returned to full consciousness days later. At a hospital in the United States, a 22-year-old man was resuscitated after 96 minutes of cardiac arrest due to overdose, with the aid of ECMO and advanced mechanical ventilation. He was discharged with preserved functional capacity. These episodes have led to a re-evaluation of traditional time limits in emergency medicine, paving the way for prolonged resuscitation protocols, especially in young patients or those with potentially reversible causes. From a scientific perspective, the brain tolerates the absence of oxygen better than previously thought, provided certain conditions are met. Preserving minimal blood flow, lowering metabolism through cooling, and blocking the inflammatory cascade post-return are the pillars of this new advanced resuscitation medicine. Each successful case provides valuable data on the neurophysiology of survival, on how the brain enters and exits liminal states, and on how clinical death can, in some contexts, be merely a reversible pause in functional life. Studying these extreme recoveries is studying the interval between the end and the restart. It is recognizing that in certain circumstances, the heart can stop for an hour, yet life still pulses, in silence, deep within the brain, waiting for the right moment to return. Few functions in the human body are as constant and crucial as breathing. The act of inhaling and exhaling not only ensures the exchange of oxygen and carbon dioxide, It also maintains blood pH, cellular metabolic function, and even the viability of consciousness itself. That's why the idea of someone living without lungs for several days seems at first glance absolutely impossible. However, in 2016, doctors at the University of Toronto documented the first clinical case of survival without any functional lungs for nearly a week. A 32-year-old woman with end-stage cystic fibrosis underwent emergency removal of both lungs due to a devastating infection. And yet, with advanced artificial support, her body remained alive, conscious, and functional until a transplant could be performed. This singular case became a milestone in intensive medicine and opened a new window into how far the human body can be sustained without its most vital organs. The procedure, known as a lung transplant with temporary absence of lungs, involved the complete removal of both lungs, followed by maintenance of the patient via ECMO, extracorporeal membrane oxygenation. This system acts as an external artificial lung. Blood is removed from the body, mechanically oxygenated, and returned, maintaining vital gas exchange while the lungs are absent. What surprised the medical team was that even without lungs, the patient could be awakened, communicate through gestures, and participate in her own care, thanks to the full support provided by the technology. ECMO fully took over pulmonary function for 6 days until a pair of donor lungs became available. From a physiological perspective, this situation represents an extreme state of assisted life. The lungs, beyond oxygenating blood, also filter small emboli, produce local hormones, activate enzymes, and influence blood pressure. Their absence forces medicine to manually assume many of these roles. In this patient's case, circulatory support machines, continuous dialysis, light sedation, and strict anticoagulation were required to prevent clots in the extracorporeal circuit. Even so, her major organs, heart, liver, kidneys, and brain, continued functioning, proving that life can be mechanically sustained far more extensively than previously thought. This clinical episode also reignited discussions about the ethical and philosophical boundaries of life, maintained by total support. When an organism no longer has lungs but remains conscious and metabolically active through machines, we are dealing with a new category of existence, partial extracorporeal life. Despite being critically ill, the patient still retained all markers of identity, cognition, and consciousness. Her brain continued functioning normally, demonstrating that, at least under ideal hospital conditions, breathing can be completely outsourced for a limited time, enabling interventions once considered impossible. Medicine has learned from this case that if other bodily functions remain stable and ECMO is initiated early, the physical absence of lungs does not necessarily mean death. This has directly impacted emergency lung transplant protocols, especially for patients with fulminant infections, severe rejection, or bilateral trauma. Today, it is known that the interval between lung failure and the arrival of a compatible donor can be managed with full ECMO, provided the environment is controlled and the medical team is highly specialized. Beyond the clinical impact, this type of support has inspired new research in bioengineering and regenerative medicine. Scientists are developing biological artificial lungs, using collagen scaffolds and stem cells to reconstruct functional respiratory tissues. The case of the woman without lungs showed that the human body can tolerate the temporary absence of complex organ functions as long as blood flow, oxygenation, and metabolic control are maintained. This opens future possibilities for staged transplants, partial lung regeneration, and even life support in extreme conditions, such as long-term space travel, military trauma, or respiratory pandemics. From a physiological standpoint, surviving without lungs for nearly a week is not just a technical feat, it's a conceptual revolution. It is proof that life can be temporarily dissociated from functions once thought non-negotiable. And with the advancement of human-machine interfaces, we may only be beginning to understand how far the human body can be sustained, repaired, and rebuilt, even when it lacks what was once considered essential. Cold water, under normal circumstances, poses an immediate threat to human life. Prolonged exposure to temperatures below 5 degrees Celsius causes rapid loss of body heat, muscular paralysis, and, within minutes, death by hypothermia or drowning. However, there are documented cases in the medical literature of individuals submerged in frozen lakes for far longer than science considers survivable, 30, 40, even 60 minutes, who were rescued with vital signs preserved or fully recovered after extended resuscitation. One of the most studied cases involved a Norwegian fisherman who fell beneath the ice during an expedition, remained submerged for over 40 minutes, and survived with virtually intact neurological function. How can the human body resist an environment that theoretically seals death within minutes? The answer lies in a precise symphony of thermal effects, emergency physiology, and advanced support systems. The key is a phenomenon known as protective hypothermia induced by cold water. Unlike hypothermia caused by wind or snow, submersion in near-freezing water leads to a rapid drop in core body temperature, especially when the victim is fully immersed. This sudden fall triggers extreme bradycardia, peripheral vasoconstriction, and a dramatic reduction in oxygen consumption by tissues, particularly in the brain. Within minutes, the body enters a state of reduced metabolism, almost like involuntary hibernation, where vital organs consume only a fraction of the energy they would require at normal temperature. This state creates a narrow but real window of opportunity in which cardiac arrest can occur without immediate neurological damage, provided rescue and rewarming happen under ideal conditions. In the case of the Norwegian fisherman, when he was pulled from the lake, he had no heartbeat or spontaneous breathing. However, his core body temperature was around 19 degrees Celsius, which allowed the emergency team to initiate resuscitation with ECMO, mechanical ventilation, and progressive rewarming. After several hours of advanced support, his heart began beating again. Days later, he opened his eyes. No cognitive deficits, no motor damage, just a prolonged silence that medicine is still trying to decipher. Science refers to this type of event as prolonged extracorporeal resuscitation under deep hypothermia, and it is only possible because cold water temporarily halts the natural cycle of cellular death. At normal temperatures, the human brain begins to suffer irreversible damage after 4 to 6 minutes without oxygen, but below 20 degrees Celsius, that window extends, in some cases, to over an hour. Synapses go dormant, ion channels shut down, and neuronal action potentials enter a standby mode. It's as if the nervous system pauses its most sophisticated functions, waiting safely for metabolism to return to operational levels. This phenomenon also depends on the quality of the aquatic environment. The water must be extremely cold, clean, and still. The absence of violent motion helps preserve physical integrity and reduces the risk of aspiration. Additionally, the victim must submerge with relatively full lungs so that residual gas exchange provides some degree of passive oxygenation before total collapse. Time submerged, exact temperature, the onset of hypothermia, and the subsequent immune response are all critical to the outcome. In trauma centers in Scandinavia and northern Canada, these cases are meticulously documented to refine emergency protocols for extreme environments. After rescue, the body rewarming process must follow strict guidelines. Passive rewarming is too slow for victims in arrest, while aggressive external warming can cause sudden vasodilation and hemodynamic collapse. For this reason, methods like internal rewarming with heated fluids, ventilation with warm air, and ECMO are preferred. These techniques mitigate the risks of reperfusion syndrome and allow organs to recover gradually. During this process, physicians carefully monitor cerebral perfusion, acid-base balance, and cardiac integrity. Often patients must remain sedated, thermally controlled, and under respiratory support for days. To medical science, each of these survivors is more than an exception. They are living proof that the line between life and death can be modulated by environmental and technological factors. Data gathered from these rescues have contributed directly to the development of cerebral preservation techniques in neurosurgery, transplantation, and even in artificial hibernation plans for space missions. More than that, these cases change the way we think about death. It is no longer a fixed point, but a gray zone, sometimes reversible, where the body may rest for minutes or hours, suspended in time, waiting for the right touch of science. Diving deep into the ocean is more than an adventure. It is an incursion into an environment where the laws of human physiology are challenged with every descending meter. For every 10 meters of depth, ambient pressure increases by 1 atmosphere. This means that at just 30 meters, the human body is under 4 times the pressure experienced at sea level. In professional, military, or accidental dives reaching 100 meters or more, this pressure can alter gas behavior in the blood, affect consciousness, and compromise the functioning of the lungs, brain, and heart. Decompression sickness, nitrogen poisoning, and lung collapse are just some of the threats. Yet divers have survived extreme pressures, some for hours, and returned to the surface with preserved function. How does the human body withstand such a hostile environment? The key to surviving great depths lies in pressure adaptation and the control of respiratory gases. As a diver descends, rising pressure causes gases, especially nitrogen, to dissolve more easily into the blood and tissues in accordance with Henry's law. Oxygen, essential for life, also becomes potentially toxic at high concentrations. That's why divers descending below 30 meters use gas mixtures like trimix, oxygen, nitrogen, and helium, to avoid nitrogen narcosis, a neurological condition akin to drunkenness that can cause confusion, euphoria, and loss of coordination. In saturation dives, common in offshore oil and deep-sea mining operations, divers live for days in pressurized chambers, gradually adapting their bodies to extreme pressure before beginning work in abyssal depths. Decompression sickness, or the bends, is one of the most studied risks. It occurs when ascent is too rapid, causing dissolved gases, mainly nitrogen, to form microscopic bubbles in the bloodstream, tissues, and joints. These bubbles trigger pain, inflammation, vessel obstruction, and in severe cases, neurological injury, paralysis, or sudden death. Standard treatment involves recompression in a hyperbaric chamber to redissolve the bubbles, followed by a controlled decompression protocol. The success of this treatment depends on how quickly it is administered and the total volume of gas released. Depth also affects the lungs and chest cavity. During descent, the volume of air in the lungs is compressed by external pressure. In dives using compressed air, this is compensated for by the regulator, which delivers gas at ambient pressure. However, in freediving without breathing apparatus, air in the lungs is compressed to the point of alveolar collapse, a phenomenon called lung squeeze. At extreme depths, capillaries can rupture, leading to pulmonary bleeding. Still, there are freedivers who reach over 100 meters using respiratory training, diaphragmatic control, and thoracic adaptations that defy known medical limits. Another major risk is oxygen toxicity, which occurs when oxygen at elevated partial pressures becomes harmful to the central nervous system. This can trigger underwater seizures and immediate risk of drowning. That's why technical divers adjust their gas mixtures carefully according to depth. Helium is used at high pressures because it is an inert gas with low density, reducing respiratory effort and minimizing narcosis risk. However, helium has a drawback. It accelerates hypothermia, as it conducts heat away from the body much faster than air. Saturation divers use heated suits and thermally controlled pressurized environments to avoid thermal collapse during extended dives. Re-entering the surface is a process that demands near-surgical precision. Decompression times can last hours depending on depth and bottom time. Mistakes during ascent are the most common and the most fatal. As a result, the majority of severe diving accidents occur during ascent rather than at maximum depth. Diving medicine has developed mathematical algorithms based on gas physics, such as the Buhlmann and RGBM models, to guide divers through safe ascent protocols and decompression stops. Extreme survival cases at great depths include the famous story of Nigerian diver Harrison O'Keefe, who survived over 60 hours trapped in an air bubble 30 meters underwater after his ship sank. The cold, dark, high-pressure environment, combined with O'Keefe's calm demeanor and controlled breathing, allowed his metabolism to slow and helped him avoid both hypoxia and explosive decompression. He was rescued by a team of saturation divers and successfully treated in a hyperbaric chamber. The diver's syndrome shows that the human body is deeply sensitive to environmental physics, but also remarkably adaptable, given the right training, technology, and strict control. Studying these limits is essential not only for divers, but also for astronauts, pilots, soldiers, and anyone operating in pressure-altered environments. The depth of the sea, silent and unforgiving, reveals that survival is possible even under tons of pressure, as long as the body and mind know how to respond, breathe, and rise. Above 8,000 meters of altitude, The human body enters a realm where life can no longer be sustained for long without artificial support. This range, found on the world's tallest mountains, such as Everest, K2 and Kangchenjunga, is known as the death zone. Here, atmospheric pressure is so low that the available oxygen drops to just 1/3 of what is found at sea level. This leads to a progressive collapse of bodily functions. Blood becomes poorly oxygenated, tissues suffer hypoxia, and the brain begins to deteriorate rapidly. Even so, there are documented cases of climbers who survived for hours or even days above 8,000 meters, many of them without supplemental oxygen, amid lethal temperatures, violent winds, and extreme deprivation. How is the human body able to endure such conditions? The answer begins with physiological adaptation to hypoxia. As one ascends gradually, the body attempts to compensate for the thinning air by increasing respiratory rate, producing more red blood cells, and releasing enzymes that enhance oxygen transport. However, acclimatization has limits, and above 8,000 meters, no adaptation is sufficient to maintain homeostasis for long. Blood oxygen saturation can drop below 60%, a level that would cause loss of consciousness in normal environments. Yet experienced mountaineers, with years of high-altitude training, can remain alert and active at such levels due to a combination of cellular plasticity, metabolic efficiency, and progressive tolerance to hypoxia. Among the most remarkable cases is that of Italian climber Reinhold Messner, the first to summit Everest without supplemental oxygen. His extreme resilience was studied by physiologists, who found that his body had an unusual capacity to maintain cerebral blood flow and minimize acidosis, even at extremely low oxygen levels. Another notable case is that of French climber Jean-Christophe Lafay, who survived 2 days on Makalu after being stranded without shelter or oxygen during a storm. His body entered a state of forced hypometabolism, reducing energy consumption to minimal levels, similar to partial hibernation seen in animals from extreme climates. Prolonged exposure to the death zone brings multiple threats. High-altitude cerebral edema, HACE, is among the deadliest. It occurs when severe hypoxia causes vasodilation in brain capillaries, leading to swelling and increased intracranial pressure. Symptoms include mental confusion, hallucinations, loss of balance, and, if untreated, coma and death. High-altitude pulmonary edema, HAPA, is also common, caused by elevated pulmonary arterial pressure, leading to fluid accumulation in the alveoli. Coughing up blood, respiratory distress, and crackling lung sounds are clear signs, often fatal if not treated swiftly. Beyond respiratory and neurological problems, the body faces deep cellular freezing. With temperatures dropping to -40 degrees Celsius and even lower wind chills, extremities are rapidly affected. Blood flow is redirected to the body's core, causing necrosis of fingers, toes, ears, and nose, often requiring amputation. Extreme survival cases in such conditions involved climbers who lost entire limbs but stayed alive through a combination of improvised shelter, state-of-the-art thermal gear, mental training to endure pain, and aerial rescue support. Another decisive factor is mental state. Oxygen deprivation directly impairs judgment, coordination, and logical reasoning, leading many climbers into disorientation. There are accounts of individuals removing their gloves, walking away from safe routes, or lying down in the snow thinking they were safe. Survival in these environments demands not only physical ability, but also a resilient psychological state, capable of distinguishing hallucination from reality, maintaining focus under pressure, and resisting the deadly temptation to rest. Many survivors describe entering an almost meditative mental state, focusing only on the next step, the next movement, without contemplating the magnitude of their situation. For medicine and physiology, survival in the death zone represents the outermost frontier of the human body, without technological support. Unlike artificial environments, such as ICUs or hyperbaric chambers, here the body is alone, facing the most hostile conditions on Earth. Studying these survivors offers clues on how the brain copes with prolonged hypoxia, how metabolism adapts to absolute scarcity, and how certain inflammatory and hormonal responses are temporarily suspended to preserve life. These cases have direct implications in areas such as cardiac surgery, using controlled deep hypothermia, astronaut preparation for thin atmosphere environments, and even research on therapies for neurodegenerative diseases. Above 8,000 meters, science observes a human body suspending its normal function in order to continue existing, if only briefly, in a place where no living being was meant to remain. Human skin is the body's largest organ and serves as a protective barrier against the external world. It prevents the entry of microorganisms, regulates temperature, retains fluids, participates in vitamin metabolism, and provides essential sensations for survival. That's why when a patient suffers third-degree burns covering more than 90% of the body's surface, the traditional medical expectation is near certain mortality. The destruction of such an extensive portion of the skin simultaneously compromises all vital functions: immunity, thermal regulation, hydration, blood pressure, electrolyte balance, and physical integrity. And yet, science has documented rare but real cases of people who have survived this level of trauma with functional recovery and, in some instances, even social reintegration. How is this possible? The first crucial factor lies in the immediate response within the first 24 hours after trauma. The body enters a state of severe hypovolemic shock caused by massive fluid loss through the burned surface. This requires aggressive fluid resuscitation with precisely calculated intravenous solutions, such as the Parkland formula. The goal is to maintain perfusion of vital organs while the body attempts to contain systemic inflammation. This initial phase is critical. Without proper support, multiple organ failure can occur within hours. Modern burn treatment units, BTUs, are equipped to respond with advanced hydration protocols, ventilatory support, continuous analgesia, and rigorous infection prevention. Infection, in fact, is the second major threat. Without skin, the body becomes an open field for bacteria, fungi, and viruses. Even with strict asepsis, broad-spectrum antibiotics, and total isolation, sepsis is almost inevitable. Survival depends on balancing antimicrobial use with preservation of residual microbiota. In top-tier centers, a layered treatment approach is used. Temporary biological dressings, such as sterilized tilapia skin, amniotic membranes, or synthetic substitutes, cover burned areas while the body prepares for grafting. In some cases, unaffected parts of the patient's own skin are used to culture keratinocytes, which are later reapplied as cell sheets, a slow but effective process. Recovery hinges on the passer body's ability to regenerate functional epithelium, but also on continuous artificial support for weeks or even months. The metabolism of a major burn patient is hypercatabolic. They burn through muscle, fat, and internal reserves at an accelerated rate. Patients can lose over 20% of their body mass in the first weeks. That's why parenteral and enteral nutrition becomes an absolute priority, using formulas rich in protein, zinc, vitamin C, and arginine, all essential for tissue regeneration. Healing is slow, irregular, and painful. It requires multiple surgeries, daily physical therapy, and intensive psychological support. Yet regeneration is possible. One of the most notable cases is that of a young American who survived with 95% of his body burned after a gasoline accident. He spent over a year hospitalized, undergoing more than 100 reconstructive surgeries, autologous grafts, and dermoepithelial prostheses. Today, he is a motivational speaker. Cases like his demand a multidisciplinary effort. Physicians, plastic surgeons, nutritionists, respiratory therapists, complex wound nurses, and psychologists work in rotation. Pain is constant and must be managed with opioids, nerve blocks, and even conscious sedation during dressing changes, which can last for hours. Emotional neuroplasticity is another essential factor. Survivors of extensive burns go through a grieving process for their own bodies. Many lose recognition of their image, tactile sensation, and facial expression. Social reintegration is challenging, especially in societies that highly value appearance. However, studies show that patients with consistent family support, spiritual faith, or defined purposes, such as returning to work, caring for children, or sharing their story, exhibit greater resilience and emotional recovery. This directly influences immune response and treatment adherence. From a biotechnology standpoint, extreme survival cases have inspired the creation of lab-grown skin. Collagen scaffolds seeded with stem cells and 3D printers that deposit cellular layers directly onto wounds. These advances are still in experimental phases, but they already offer alternatives for patients with burns so extensive that no donor skin is available. Smart dressings that release antibiotics, growth factors, and infection sensors are also revolutionizing how BTUs operate. To survive without skin is to survive without the boundary between self and world. It is to live in a state of maximum vulnerability, where every centimeter of the body aches, loses heat, loses water, and remains exposed to death. And yet, with science, technique, humanity, and time, the body can be reborn, one graft at a time, rebuilding its integrity upon the memory of destruction. Fire, since the dawn of humanity, has symbolized transformation, but also total destruction. In urban settings, fire-related disasters can consume structures, vehicles, and human bodies within minutes, reaching temperatures that easily exceed 100 degrees Celsius in enclosed environments. Under such conditions, survival is statistically unlikely, yet there are real, well-documented reports of people who emerged alive from house fires, vehicle explosions, or blazing structural collapses, sometimes with minor injuries or even unscathed. How can the human body, a living and vulnerable tissue, endure something capable of vaporizing metals and calcining concrete structures? The first explanation lies in the uneven thermal distribution of fires. Even in the most devastating scenarios, fire behaves irregularly. It forms zones of extreme heat, known as primary flashpoints, interspersed with pockets of cooler air created by upward drafts, external ventilation, or physical obstacles. In many cases, people survive by being precisely in these less hostile microenvironments, such as under bathtubs, behind heavy furniture, or within wall cavities. These invisible refugees can mean the difference between life and death, often going unnoticed by firefighters. Another crucial variable is the duration of thermal exposure. The human body can withstand extremely high temperatures for brief periods, as long as the skin does not remain in prolonged contact with the heat source. A phenomenon known as flashover, the moment when all combustible materials in a room ignite simultaneously, represents the peak danger. However, if an individual is moving, has their skin covered, and escapes the thermal center within seconds, there is a real chance of escaping without deep burns, even if clothing or hair is consumed by the flames. Notable cases include survivors of burning vehicle accidents who managed to escape the wreckage after explosions. One example was recorded in the United States, where a driver trapped in wreckage survived for 4 minutes inside a burning car, protected by an airbag system and an aluminized rescue blanket. The heat carbonized the seats and melted the dashboard, but the lower interior zone of the vehicle remained at tolerable temperatures long enough. When extracted, the driver had only first-degree burns on the legs. Smoke inhalation, paradoxically, is the deadliest factor in fires, even more than the heat itself. Gases like carbon monoxide, hydrogen cyanide, and solid particles cause intoxication in seconds, leading to unconsciousness before the flames reach the body. Some survivors report losing consciousness from inhalation and waking up hours later already rescued, unaware they narrowly escaped lethal anoxia. Others, by covering their mouths and noses with wet cloths and staying low to the ground and where smoke is less dense, manage to remain conscious long enough to find shelter or wait for rescue. There's also the phenomenon of selective combustion. In collapsed structures, fire tends to consume objects and surfaces with higher flammability first. A person trapped in a concrete gap between beams may be spared by the very architecture around them. In some cases, bathrooms and water tanks provide improvised thermal refuge, and there have been reports of victims who threw themselves into filled bathtubs or sinks, waiting for the fire to subside. Even more unlikely but documented are cases of metabolic refractoriness to heat. Under extreme stress, the body enters thermal collapse without dying, keeping core functions on the brink of failure, but recovering after cooling and advanced support. For forensic scientists, analyzing survival in extreme fires provides key data on flame behavior, gas toxicology, and biological tissue resistance under high heat. These insights guide the development of safer materials, such as fire-resistant clothing made from aramid fibers, like Nomex, smoke ejection ventilation systems, and intelligent evacuation algorithms for public buildings. In medicine, the study of survivors has helped improve burn unit protocols, acute hydration formulas, and infection control for severe burn victims. Resistance to fire is not a biological invincibility. It's a delicate equation of luck, physics, and physiology. But these real accounts of survival remind us that, even surrounded by flames, the human body can still find cracks, cool zones, critical seconds, and the chance to continue existing beyond the visible destruction. The idea of a partial decapitation, in which an individual's head becomes partially detached from the body or is internally displaced without complete rupture of neurological pathways, sounds like something drawn from medical fiction. However, science has documented clinical cases where, following violent accidents, the base of the skull dislocated from the cervical spine, resulting in a condition known as internal or orthopedic decapitation. In these scenarios, the bones connecting the head to the body are separated, but soft structures, the spinal cord, trachea, blood vessels, and connective tissues remain partially intact. In certain cases, with immediate surgery and stabilization, the patient not only survived, but regained motor and cognitive functions. How can the human body endure such an extreme trauma, typically considered instantly fatal? The explanation begins with the anatomy of the occipito-cervical complex, where the base of the skull articulates with the first cervical vertebra, atlas, and the second, axis. In high-energy collisions, such as car crashes or vertical falls, the weight of the head can generate a shear force so intense that it mechanically separates these joints, causing instability of the craniovertebral junction. If the spinal cord is not severed and the major blood vessels withstand the strain, the brain can continue receiving blood, and motor commands can still travel through partially functional nerve fibers. The body then enters an extremely precarious state, but remains alive. Clinical cases such as that of Jordan Taylor, an American child who suffered complete internal decapitation in a car accident at the age of 9, have been deeply studied. His head was literally separated from the body in skeletal terms, but soft tissues prevented total rupture. After emergency surgery to realign the spine, internal fixation with rods, and absolute rest, Jordan not only survived, he walked again months later. Another case occurred in Germany, involving an adult cyclist hit by a truck. The injury was so severe that doctors had to suspend his skull with traction while reconstructing the cervical base. Miraculously, the spinal cord had not been torn. Science classifies such events as traumatic atlanto-occipital dislocations, and the survival rate is below 30%. However, with an immediate immobilization, intracranial pressure control, reconstructive surgery, and assisted ventilation, life can be preserved. During the first hours, the main risk is vascular injury, especially to the vertebral artery, which supplies the brainstem. The slightest displacement can cause cerebral ischemia, coma, or sudden death. For this reason, trauma protocols for suspected internal decapitation demand absolute neck immobilization, use of rigid cervical collars, and urgent evaluation with high-resolution CT scans. During recovery, the focus shifts to neuromotor rehabilitation. Since neural circuits may remain intact but lack proper motor coordination, patients must relearn how to support the weight of their head, coordinate movements with unstable balance, and cope with potential sensory deficits. Pain is constant, and in some cases there is a need for opioid support, anesthetic blocks, and intensive physical therapy. Despite this, case reports show that even after catastrophic cervical separation, the body finds ways to reintegrate its most basic functions, as long as neurological signals can still travel through some viable path. From a scientific perspective, these survivors are of particular interest to neurosurgeons and trauma specialists. Data from such cases help in developing more effective cervical stabilization devices, minimally invasive techniques for vertebral fusion, and risk algorithms for victims of closed cervical trauma. Furthermore, these cases underscore the importance of accurate triage in car accidents, as internal decapitation is often invisible externally, yet can become fatal within minutes, if not promptly identified. Symbolically, surviving this type of injury demonstrates that, even in the face of a literal rupture between the center of thought and the rest of the body, life can persist, and the body can rebuild its lost connection. There is no more direct metaphor for the struggle for wholeness than witnessing a head once again supported by a body that refused to die. In 1848, a young railroad worker named Juan Phineas Gage survived one of the most famous neurological accidents in the history of medicine. A metal rod over 1 meter long pierced his skull from bottom to top, entering through his left cheek and exiting through the top of his head, destroying part of the frontal lobe of his brain. Against all expectations of the time, and even by today's standards, he not only survived, but remained conscious during rescue and spoke with doctors upon arriving at the hospital. Gage's case became a landmark in neuroscience, demonstrating that the human brain, even when deeply damaged, can reorganize itself, adapt and continue functioning. And he wasn't alone. Over the centuries, other survivors with catastrophic brain injuries have shown recovery capabilities that defy classical models of neurology. Unlike other organs, the brain does not regenerate fully, but it has a phenomenon called neuroplasticity, the ability to relocate cognitive and motor functions from a damaged region to another. This happens more intensely in children and young people, but is also present in adults. In extreme cases like Gage's, areas related to personality, planning, impulse control and judgment were damaged, yet he could still walk, speak, recognize people, and perform tasks. What was lost, as later documented, was part of his emotional identity and behavioral regulation. He became more impulsive, aggressive and unstable, changes now known to be associated with the ventromedial prefrontal cortex. More recently in 2012, a case caught the medical community's attention. A Brazilian construction worker was struck by a 2-meter-long metal bar that fell from an upper floor and penetrated his skull. The rod pierced regions of the motor cortex and part of the corpus callosum, yet he arrived at the hospital awake and lucid. The surgery to remove it was extremely risky, and recovery took months of therapy. But surprisingly, he regained speech, partial coordination, and could walk with assistance, showing that, even in open brain injuries, the body can find alternative paths to preserve basic functions. Survival in these scenarios depends on multiple factors. One of the most important is the trajectory of the perforation. If the penetrating object avoids major vessels like the middle cerebral artery and vital structures like the brainstem, the chances of survival increase dramatically. Furthermore, the speed of entry directly impacts the level of damage. Objects that penetrate slowly cause less intracranial shockwave than high-velocity projectiles like bullets. That's why cases involving rebar, rods or tree branches, all documented in medical literature, tend to have better outcomes than ballistic injuries. The inflammatory response and infection risk are equally critical. The brain is highly sensitive to bacterial invasion, and even minor contamination can lead to meningitis or fatal brain abscesses. That's why patients who survive the initial injury must be treated with broad-spectrum antibiotics and undergo continuous monitoring for weeks. In many cases, bone fragments and foreign objects remain in the brain tissue and are naturally encapsulated by glial cells, support cells that literally build internal protective barriers around the damage. These extreme events cause lasting changes, not only in the brain but in the patient's identity. Studies with survivors of penetrating injuries reveal deep alterations in self-perception, empathy, emotional regulation, and even existential purpose. Some report near-death experiences, memory lapses, vivid dreams, or temporary synesthesia. For neuroscientists, these experiences are valuable because they reveal how the brain operating in marginal states, reconstructing circuits under pressure, like an entire city relocated after an earthquake. Cases like Phineas Gage's continue to be studied today using modern techniques such as 3D reconstruction, functional neuroimaging, and neural simulations. They have directly influenced fields such as neuropsychology, cognitive rehabilitation, epilepsy surgery, and even criminal behavior studies, since they show that damage to specific brain areas can radically alter morality and decision-making. In a world where traumatic injuries are among the leading causes of death and disability, understanding how the mind survives this type of wound means understanding the deepest mechanisms of human identity. These survivors with iron rods through their skulls or missing brain sections show us that the mind is more than organized flesh. It is a dynamic system capable of reorganizing under extreme pressure. And even when the envelope of consciousness is violated, something within us keeps fighting to think, to remember, to react, and to survive. Most medical textbooks teach that the human body can survive between 30 and 60 days without food, as long as adequate hydration is maintained. Beyond a certain point, the body enters severe catabolism, breaking down muscle, fat, and even non-essential tissues in search of energy. Starvation death, therefore, appears to be an inevitable process after several weeks of total fasting. However, there are documented cases in science of people surviving 70, 80, 100, and even 382 days without eating, as occurred with a Scottish patient under hospital supervision. How can the human body endure the total absence of food for so long without undergoing systemic collapse? What happens, step by step, to the body's systems during prolonged fasting? It all begins with the depletion of circulating glucose. In the first 6 to 24 hours without food, the body consumes glycogen stored in the liver and muscles. This temporarily supplies the brain, which initially relies exclusively on glucose. Once these stores are exhausted, the body enters ketosis, a metabolic state where fat is broken down into fatty acids and ketone bodies. Muscles are initially preserved while the liver takes over the task of producing alternative energy. The brain, which rejects most organic fuels, adapts to the presence of ketones and begins using them partially, lowering its glucose demand. This metabolic shift is essential for survival beyond the first week. However, during prolonged fasting, body fat is eventually depleted. The rate of loss depends on the initial weight. An obese person can survive far longer without food than a lean individual. The most famous case is Angus Barbieri, a Scottish man who in 1965 survived for 382 days without consuming solid food. Under medical supervision, he received only water, coffee, vitamins, and electrolytes. By the end of the fast, he had lost 125 kilograms and showed normal levels of glucose, electrolytes, and liver function. This feat was documented in the Postgraduate Medical Journal and remains a unique case of successful extreme therapeutic fasting. Other cases involve survivors of disasters such as earthquakes, avalanches, or entrapments, where people went 2 to 4 weeks without food, often with minimal hydration. Under extreme conditions, the body enters deep conservation mode, lowering basal metabolic rate, core body temperature, and cellular energy consumption. The heart rate slows, digestion halts entirely, menstruation stops, and neurological activity enters a lethargic state. Though dangerous, this condition can prolong life if there is some intake of water, even minimal. Without hydration, the average survival time drops sharply to less than 10 days. Death by starvation generally results from cardiac failure, opportunistic infection, extreme hypoglycemia, or arrhythmias caused by imbalances in potassium and magnesium. However, when fluid and electrolyte intake is maintained, as in Barbieri's case, the body can delay systemic failure for months, provided it is monitored. The greatest risk arises during refeeding. After long periods of fasting, reintroducing food can trigger refeeding syndrome, a potentially fatal condition caused by the rapid absorption of nutrients and sudden intracellular electrolyte shifts, resulting in hyperphosphatemia and arrhythmias. Science is now exploring therapeutic fasting more deeply, not as an extreme diet, but as a strategy for metabolic resilience. Controlled protocols of intermittent fasting and calorie restriction have shown benefits in metabolic, neurodegenerative, and inflammatory diseases. However, none approach the extremes of absolute fasting. These events are considered edge case human experiences, useful only for understanding adaptation mechanisms in extreme states, such as chronic hunger, coma, or survival in hostile environments. From an evolutionary perspective, the ability to fast for long periods was an adaptive advantage. Our hunter-gatherer ancestors did not eat at regular intervals, and the body developed sophisticated ways to conserve energy, recycle internal proteins, and resist scarcity. Autophagy, for instance, the cellular process that digests internal structures for energy, is strongly activated during fasting and is linked to cellular longevity and tumor prevention. Surviving for months without food is possible only under very specific conditions: high initial fat reserves, precise electrolyte supplementation, rigorous medical monitoring, and careful refeeding. For most people, this path is unreachable and dangerous, but the documented cases show that the human body is an extraordinarily adaptable system, capable of rewriting its metabolic rules when there is no more food, only waiting. When the human body's core temperature drops below 35 degrees Celsius, a state of mild hypothermia begins. But there are documented cases in which people have survived with core temperatures below 20 degrees Celsius, technically considered incompatible with life. These extreme situations, where the body enters a near-suspended animation state, challenge the known limits of physiology. Cases like that of Norwegian Anna Bogenholm, who in 1999 became trapped under ice with a recorded body temperature of 13.7 degrees Celsius and still survived without severe neurological damage, are analyzed with fascination by doctors around the world. How can the human body remain alive under such intense freezing when even breathing and heartbeat nearly vanish? The key lies in the speed of cooling and the natural protection against anoxia. When the body cools rapidly, cellular metabolism slows down on all fronts. This reduces oxygen consumption, preventing cellular collapse due to hypoxia. The brain, which under normal conditions suffers brain death after 4 to 6 minutes without oxygen, can survive for up to 60 minutes or more when cooled below 20 degrees Celsius. This principle is even applied in complex cardiac surgeries, where patients are induced into deep hypothermia so the heart can be safely stopped for extended periods. In accidental cases like Anna's, hypothermia occurs through extreme exposure. She fell into a frozen stream while skiing and remained submerged for 80 minutes. During rescue, she showed no detectable vital signs. At the hospital, she was connected to an extracorporeal circulation machine, ECMO, which gradually rewarmed her blood. This technique allowed for safe and reversible rewarming of her organs. After days in an induced coma, she awoke with intact brain function. The secret to her survival lies in the combination of rapid cooling, preserved cerebral perfusion, and absence of severe physical trauma. The physiology of extreme hypothermia involves multiple stages. In mild hypothermia, 32 to 35 degrees Celsius, the body reacts with shivering peripheral vasoconstriction and increased heart rate. In moderate hypothermia, 28 to 32 degrees, shivering ceases, consciousness is altered, and metabolism slows. Below 28 degrees, severe bradycardia, ventricular arrhythmias, and risk of cardiac fibrillation occur. Below 20 degrees, many functions become undetectable. Breathing becomes imperceptible, pupils dilate, and the EEG may show near-flat activity. Despite this, life persists in a latent state and can be restored if rewarming is gradual and controlled. The principle that makes this possible is thermal preservation of the central nervous system. The brain, protected by cerebrospinal fluid and bone layers, is relatively resistant to superficial freezing. Intracellular water, when crystallizing slowly, can cause cellular rupture. However, if cooling is deep and fast enough, cells enter a metabolic hibernation state before structural damage occurs. For this reason, in many cases of children drowning in frozen lakes, the chances of survival without lasting damage are higher than in warm water drownings. Cases like that of Mitsutaka Uchikoshi in Japan are equally remarkable. He fell unconscious on a mountain and was found 24 days later with a body temperature of 22 degrees Celsius. During that time, his body entered a near hibernation state with minimal energy consumption. He survived thanks to the cold environment, which prevented systemic collapse and drastically reduced his metabolic demands. This has led researchers to explore whether artificial induction of deep hypothermia could be used in medical emergencies, such as severe trauma, cardiac arrest, and high-risk neurosurgery. Today, hospital protocols for therapeutic hypothermia are common in ICUs for patients with cardiac arrest or brain trauma. Induced cooling to between 32 and 34 degrees Celsius helps preserve the brain while doctors stabilize organs. Science is also exploring applications for space missions, inducing hypothermia to slow metabolism during long interplanetary journeys as a form of cryosleep. Studies with guinea pigs and rats have shown that certain neurotransmitters, such as GABA, can be manipulated to induce torpor-like states. Being frozen alive and surviving without sequelae is one of the most extreme examples of biological adaptation ever recorded. It shows that under specific conditions, the human body can temporarily suspend classical signs of life, heartbeat, breathing, consciousness, and still return intact to the warmth of existence. In this context, the line between life and death is not a fixed point, but a flexible boundary shaped by temperature, time, and metabolism. The human heart, when it stops beating, marks the official onset of clinical death. Traditionally, the absence of pulse, respiration, and neurological response for more than 5 to 10 minutes leads to brain death, which is considered irreversible. However, in recent decades, doctors around the world have documented cases of people who remained with no heartbeat for 45, 60, and even 120 minutes, and were later resuscitated with preserved neurological function. These events, once thought impossible, have profoundly changed the boundaries of emergency medicine and our understanding of what it means to be dead. How does science explain the return to life after a prolonged cardiac arrest? And how can the body tolerate so much time without apparent oxygen? The first explanation lies in the relationship between body temperature and metabolism. In many of these cases, the patient was hypothermic at the time of cardiac arrest, which drastically reduced the brain's oxygen consumption. This was observed in cold water drowning accidents, cardiac surgeries involving induced hypothermia, or individuals exposed to extreme cold before the arrest. Cooling slows cellular metabolism to the point of delaying cell death processes. Thus, even without blood circulation, the brain enters a kind of functional hibernation, allowing neurons to withstand hypoxia for much longer than normal. One of the most emblematic cases occurred in 2001, when Anna Bogenholm, previously mentioned for having been frozen under ice, had no heartbeat for nearly 2 hours. Her body was recovered with a core temperature of 7 degrees Celsius, and after being connected to an ECMO machine, extracorporeal membrane oxygenation, her blood was gradually rewarmed and recirculated. Circulation resumed after more than 60 minutes of absolute asystole, a duration that under normothermic conditions would result in brain death. Yet she survived without severe neurological sequelae, proving that death, in such cases, is not a fixed line, but a grey zone defined by temperature and artificial support. Similar cases occurred with victims of prolonged cardiac arrest in urban settings, where cardiopulmonary resuscitation, CPR, was applied continuously for more than an hour. In 2014, a man in Spain was resuscitated after 96 minutes of cardiac arrest thanks to a combination of manual CPR, repeated defibrillation, oxygenation with ECMO, and induced therapeutic hypothermia. Doctors maintained resuscitation under the belief that hypothermia was protecting the patient, and they were right. Today, advanced protocols in specialized centers suggest that prolonged CPR should be continued for up to 2 hours in selected cases, especially when protective factors are present. Neuroscience also shows that brain death is not immediate. After cardiac arrest, neurons begin a progressive degenerative process, which can be reversed if circulation is re-established in time. The challenge is to prevent what is known as reperfusion syndrome. When oxygen returns to damaged cells, it can trigger a massive release of free radicals, causing inflammation and accelerated cell death. For this reason, rewarming and reoxygenation must be done very slowly, often involving calcium channel blockers, antioxidants, and strict control of blood pressure and oxygenation. Prolonged arrest cases have also driven the development of automated CPR devices, such as the Lucas and Autopulse, which provide consistent chest compressions for hours without human fatigue. These machines have increased survival rates in out-of-hospital emergencies, especially when combined with automated external defibrillators, AEDs. In hospitals, the use of ECMO has radically transformed the concept of resuscitation. Patients who would previously have been declared dead are now candidates for full support, with entirely artificial circulation and oxygenation until the body recovers. From a philosophical and ethical standpoint, these events raise profound questions. When is a person truly dead? When vital signs cease? Or when there is no longer any reversibility, even with technology? Extreme cases of returning to life suggest that death, in many contexts, is not an absolute point, but a process, reversible up to a certain metabolic and technological threshold. This has direct implications for decisions regarding organ donation, emergency triage protocols, and the limits of intensive care. The heart can stop, the brain can fall silent. But science has shown that under certain conditions, life is not a broken line. It is a curve that can descend to its depths and rise again. Even when everything seems to have ceased, the body, if cooled, protected, and precisely reanimated, can return, and with it, consciousness, memory, and the chance to continue existing. Between the limits of physical survival and the concept of death, there exists a scientific gray zone that challenges traditional definitions of biology. These are cases in which the human body spontaneously enters states of physiological suspension, extremely rare phenomena in which all vital signs become virtually undetectable, yet death does not actually occur. Although often associated with popular culture or spiritual narratives, science recognizes some of these events as real and documentable. In hospitals, morgues, and emergency situations, there are official records of individuals who were declared dead, only to return to life minutes or even hours later, surprising medical teams, defying protocols, and expanding the boundaries of what we call life. This phenomenon is known in medicine as Lazarus syndrome, an extremely rare condition in which spontaneous return of circulation occurs after failed resuscitation attempts. The name comes from the biblical figure Lazarus, resurrected by Jesus after 4 days dead, but in scientific terms, it refers to cases in which a patient's heart starts beating again on its own, minutes after CPR has been stopped. There are dozens of cases documented in medical journals, with autopsies halted at the last moment due to sudden signs of pulse. The exact cause is not yet fully understood, but suspected mechanisms include gradual accumulation of thoracic pressure, reversing vascular obstructions, or spontaneous correction of metabolic imbalances. Other cases involve small children who fell into frozen lakes and were declared dead after extended periods underwater, but upon being rewarmed, returned to life with little or no neurological damage. This is possible because, unlike adults, the child's body responds to cold with more rapid and intense vasoconstriction, channeling blood to vital organs and drastically reducing metabolism. This creates a kind of biological suspension, a functional pause of the organism in which physiological time nearly halts. The concept of suspended animation, once confined to science fiction, finds its closest real-world counterpart in these scenarios. In other contexts, the body enters metabolic suspension due to extreme circumstances, lack of oxygen, severe trauma, deep hemorrhagic shock. In cases of massive abdominal trauma, for example, the body may drastically reduce peripheral perfusion and redirect all blood flow to the brain and heart. This allows a person to remain in a near-total state of hypoperfusion for over an hour, with minimal detectable activity, yet still alive. In modern battlefields, this knowledge has led to the development of emergency preservation techniques, such as direct cooling of the chest or intentional collapse of circulation to buy time until surgery can be performed. Science is also investigating species that do this naturally. Certain mammals hibernate for months, with heart rates reduced to 2 beats per minute and body temperatures near freezing. The black bear, for instance, can go 5 to 7 months without eating, drinking, urinating, or defecating, in a state of near-complete organic suspension. Researchers study these adaptations for potential applications in human medicine, especially in organ transplantation, severe trauma, or space travel. The goal is to induce a controlled state of hibernation, in which the body is maintained between life and death, preserving tissues until medical intervention becomes possible. Cases of survival with no detectable vital signs for over 60 minutes, particularly in young or cold-exposed individuals, demonstrate that death, contrary to popular belief, is not an instant but a reversible process under specific conditions. The body, when adequately preserved, can remain silent for extended periods and then resume activity with external assistance. It's no coincidence that modern clinical death protocols now require complete absence of circulation, ventilation, brain activity, and absolute irreversibility. In other words, death is, more than ever, a legal, technological, and situational definition. These accounts, while rare, are not miracles. They are manifestations of a biology with far deeper and more sophisticated defense mechanisms than previously believed. In times of war, disaster, and medical crisis, understanding these boundaries has saved lives that would have been abandoned under old protocols. The human body, after all, does not die all at once. It negotiates with death, resists, falls silent, and sometimes waits for the right moment to return.